James Webb finally looked into Sagittarius A. What it saw shocked scientists. For decades, Sagittarius A star was invisible. Now James Webb has exposed it, and the behaviour surrounding this black hole is forcing astronomers to rethink what's happening at the centre of our galaxy. The invisible giant at the centre of the Milky Way. For most of human history, the centre of the Milky Way was not a place of discovery. It was a blind spot. From Earth, when you look toward the heart of our galaxy, you don't see stars packed tighter than anywhere else in the sky. You don't see light pouring out from a powerful core. You don't see anything that hints at extreme gravity or cosmic violence. What you see instead is darkness, not because nothing is there, but because something is in the way. Between us and the galactic centre lies tens of thousands of light years of dust, gas and debris. Thick molecular clouds scatter and absorb visible light almost completely. Optical telescopes, no matter how powerful, hit a wall long before they reach the Milky Way's core. For decades, astronomers knew this region mattered. Galaxies tend to organise themselves around massive centres. Spiral arms curve around something dominant. Star motion hinted at a gravitational anchor buried deep inside. But knowing something was there and proving what it was are two very different things. The breakthrough did not come from visible light. It came from radio waves. In the early 1970s, radio astronomers scanning the sky noticed something strange. From the direction of the constellation Sagittarius, right where the Milky Way's disk is thickest, a compact radio source stood out against the background. It wasn't bright in the way stars are bright. It didn't flicker like pulsars. It didn't spread out like nebulae. It was tight, dense, persistent. The source was named Sagittarius A, following standard astronomical naming conventions. But inside that radio-emitting region was something even more compact. A pinpoint-like core that seemed to dominate the signal. That core became known as Sagittarius A star. In physics notation, an asterisk often indicates something special or excited. In this case, it marked a radio source that didn't behave like anything else nearby. At the time, no one rushed to call it a black hole. Black holes, especially supermassive ones, were still theoretical objects to most astronomers. The idea that an entire galaxy could orbit a single collapsed object was controversial. There were alternatives: dense star clusters, exotic matter concentrations, or unknown astrophysical phenomena. Sagittarius A star was intriguing, but radio data alone couldn't settle the question. To prove what it was, scientists needed motion. They needed to see how stars behaved near it. And for that, they needed to watch the invisible. The real transformation in our understanding of Sagittarius A star began decades later, not with one telescope, but with patience. Two major observatories took on the same long-term challenge independently: the Keck Observatory in Hawaii and the Very Large Telescope, VLT, in Chile. Both were equipped with powerful infrared capabilities, crucial for peering through galactic dust, and both committed to observing the same region of sky year after year. What they focused on were not Sagittarius A star itself, which remained invisible in infrared, but the stars around it. At the galactic centre, stars are packed densely. Many of them move fast, much faster than stars in our local neighbourhood. Some race through space at thousands of kilometres per second. These stars became known as S-stars. By tracking their positions precisely over time, astronomers began reconstructing their orbits. And those orbits told a startling story. Some of these stars complete full orbits in just 15 to 20 years, an incredibly short time for stars moving around a galactic centre. Their paths are not circular and gentle. They are elongated, extreme, and tightly bound. One star in particular, known as S2, became a cornerstone of the case. S2 swings incredibly close to Sagittarius A star at its nearest approach, closer than Pluto ever comes to the Sun. And yet it survives. Its speed increases dramatically at that point, reaching several % of the speed of light. Only one thing could explain that motion. All of that mass, millions of times the mass of the Sun, had to be concentrated in a region no larger than our solar system. Not spread out, not clustered stars, not anything with physical size. A black hole was no longer speculative, it was required. From these stellar orbits, astronomers could do something extraordinary: weigh the invisible. Using Kepler's laws and relativistic corrections, the mass enclosed within the star's orbits was calculated again and again. The numbers converged. At the centre of the Milky Way sits an object with a mass of approximately 4.3 million suns, not billions, like the black holes in quasars, not thousands, like stellar remnants, millions, tightly packed into an unimaginably small volume. The scale of this object is deceptive. A black hole with 4.3 million solar masses does not sprawl across the galaxy. Its event horizon, the point beyond which nothing escapes, is only about 12 million kilometers across. That sounds huge until you compare it to astronomical distances. The Earth is 150 million kilometers from the Sun. The diameter of Earth's orbit is 300 million kilometers. Sagittarius A star could fit comfortably inside that space. And yet, this compact object governs the motion of stars tens of thousands of light years away. This extreme mismatch, enormous mass, tiny size, is the defining fingerprint of a supermassive black hole. By the early 2000s, the debate was effectively over. Sagittarius A star was accepted as the supermassive black hole at the centre of the Milky Way, but accepting what it was did not mean understanding how it behaved. In fact, the more scientists learned about Sagittarius A star, the stranger it seemed, because by all appearances, it was quiet. When astronomers think of supermassive black holes, they often think of quasars. Quasars are among the brightest objects in the universe. They blaze across billions of light years, outshining entire galaxies. Their black holes consume vast amounts of matter, forming luminous accretion disks and launching jets that stretch for thousands of light years. Sagittarius A star looks nothing like that. Despite its mass, it emits very little energy. There is no brilliant disk visible in optical light, no towering relativistic jets, no overwhelming radiation pouring into space. Measurements showed that Sagittarius A star accretes matter at an extremely low rate. Compared to active galactic nuclei, it is practically starving. Stars near the centre shed material through stellar winds. Gas clouds drift inward occasionally. But very little of that material ends up falling cleanly into the black hole. What does fall in releases surprisingly little radiation. In X-rays, Sagittarius A star is faint. In visible light, it's invisible. In gamma rays, it's subdued. By black hole standards, it barely whispers. This led to a classification that stuck for years. Sagittarius A star is dormant. Not dead, not gone, just inactive. This wasn't an assumption. It was based on observations across multiple wavelengths using the best instruments available at the time. Compared to quasars and active supermassive black holes, Sagittarius A star appeared inefficient and calm. And that calmness shaped how scientists thought about black holes like it. Supermassive black holes exist on a spectrum. At one extreme are active galactic nuclei, black holes fed by thick disks of gas and dust. These systems glow intensely, often dominating their host galaxies. At the other extreme are dormant black holes, massive objects with little available fuel. Sagittarius A star was placed firmly in the second category. It had the mass, it had the gravity, but it lacked the fireworks. This made sense in context. The Milky Way is a mature galaxy. Its central region doesn't contain vast reservoirs of cold gas spiraling inward. There are no recent major galactic collisions funneling matter toward the core. Without fuel, even the most massive black hole cannot shine. For years, Sagittarius A star became the textbook example of a quiet supermassive black hole. An anchor, not an engine. But this interpretation relied heavily on what astronomers could see. And what they could see was limited. Every observation of Sagittarius A star before James Webb had to fight three major obstacles. The first was dust. The galactic center is wrapped in thick interstellar dust clouds that absorb visible and ultraviolet light almost completely. Optical telescopes, no matter how large, are effectively blind to the region. Infrared helps, but only to a point. The second obstacle was Earth's atmosphere. Even the best ground-based telescopes look through layers of air that absorb, scatter, and distort incoming signals. Adaptive optics can correct some of this, but not all. Certain infrared wavelengths simply never reach the ground. The third obstacle was time. Most observations of Sagittarius A star were snapshots, minutes or hours of data separated by days, months, or years. Long, uninterrupted monitoring was rare and technically difficult. If Sagittarius A star changed rapidly, if its behavior was subtle, if its most important signals occurred in wavelengths partially blocked by Earth, then scientists wouldn't see them. Not because they were careless, not because they misunderstood black holes, but because the universe was operating just outside their window. Sagittarius A star wasn't necessarily inactive, it was unresolved, and for decades that distinction went unnoticed. Why Sagittarius A star was branded quiet. By the time Sagittarius A star was accepted as a supermassive black hole, the most unsettling question was no longer what it was, but why it behaved so differently from what theory and observation seemed to promise. In the public imagination, black holes were cosmic destroyers, objects that swallowed everything around them and announced their presence with violence. In professional astronomy, the image was more refined, but no less dramatic. Supermassive black holes, especially those sitting at the centers of galaxies, were expected to be engines. They were expected to glow, to radiate, to announce themselves through energy released as matter fell inward and heated up. Sagittarius A star did none of that in any obvious way. What scientists saw instead was restraint. Compared to active galactic nuclei, the center of the Milky Way looked underwhelming. The black hole's mass was undeniable, but its output was not. When astronomers measured how much radiation was coming from the region immediately around Sagittarius A star, the numbers were startlingly low. In X-ray observations, the emission barely rose above background levels. In optical wavelengths, nothing penetrated the dust at all. Even in infrared, where some of the galactic center could finally be seen, Sagittarius A star itself refused to stand out as a dominant source. This led to a critical assumption that shaped decades of thinking. Black holes shine because matter falls into them. If Sagittarius A star wasn't shining, then it must not be eating very much. And when scientists estimated how much material was actually reaching the event horizon, the conclusion seemed clear. The accretion rate was tiny compared to what was seen in quasars. Instead of consuming whole clouds of gas, Sagittarius A star appeared to be surviving on scraps, thin streams of material shed by nearby stars, most of which never made it all the way in. In other galaxies, supermassive black holes often sit inside thick, luminous accretion disks that glow intensely as friction and compression heat the gas to extreme temperatures. Sagittarius A star showed no such structure. There was no bright disk radiating across the electromagnetic spectrum, no obvious jets blasting particles outward at near-light speed, no telltale signatures of sustained, efficient feeding. In the language of astrophysics, Sagittarius A star was radiatively inefficient. Gravity was present, but energy release was not. This inefficiency became the core of the quiet label. Astronomers were not being dismissive. They were describing a measurable reality. Compared to active black holes that convert a significant fraction of infalling mass into radiation, Sagittarius A star converted almost nothing. Matter approached, heated up briefly, and then seemed to vanish without producing much light. The black hole was massive, but the process around it appeared lethargic. The contrast became even sharper when Sagittarius A star was placed alongside quasars. Quasars are powered by supermassive black holes that are actively feeding, often triggered by galaxy mergers that dump enormous amounts of gas toward the center. These black holes don't just glow, they dominate their galaxies. Their light can outshine hundreds of billions of stars combined. They produce strong X-rays, intense ultraviolet radiation, and radio jets that can stretch far beyond the galaxy itself. Sagittarius A star had none of this. There was no evidence that it had ever been a quasar in the recent cosmic past, at least not within the observational record available at the time. The Milky Way showed no signs of being shaped or disrupted by powerful outflows from its core. Star formation in the galaxy continued without obvious interference from central activity. Everything pointed to a black hole that was present but largely inactive. This comparison hardened scientific expectations. If Sagittarius A star was not behaving like the black holes that defined the field, then it must represent the opposite end of the spectrum, a dormant, supermassive black hole, a gravitational anchor, not a cosmic furnace. This idea fit neatly into models of galaxy evolution. As galaxies age and lose their gas, their central black holes calm down. Sagittarius A star was simply doing what old black holes do. But this interpretation rested heavily on what instruments could detect and what they consistently failed to detect. X-ray telescopes, such as Chandra, did occasionally catch brief flares from the direction of Sagittarius A star. These events were short-lived and rare, often lasting only a few hours. They were interpreted as minor disturbances, small clumps of gas briefly heating up before disappearing. Importantly, these flares were not frequent enough nor energetic enough to challenge the idea of overall quietness. They were treated as exceptions, not indicators of persistent activity. Radio observations showed steady emission, but radio waves alone could not reveal the detailed physics of what was happening near the event horizon. Radio data suggested structure, but not motion. Presence, but not process. Without the ability to resolve fine-scale changes over time, astronomers could not tell whether Sagittarius A star was dynamically active on short timescales. This left a large gap in understanding. The black hole's environment was being inferred indirectly, through models that assumed relative stability. If nothing dramatic was observed, then nothing dramatic was assumed to be happening. The absence of bright, sustained emission became evidence of inactivity, rather than a limitation of perspective. The instruments themselves reinforced this belief. Ground-based observatories, no matter how advanced, were bound by Earth's atmosphere. Certain infrared wavelengths, especially those sensitive to warm and hot plasma near black holes, are absorbed or distorted before they ever reach a detector. Even when observations were possible, they were often fragmented. A few hours of data here, a short observing window there. Long-term continuous monitoring was nearly impossible. This meant that if Sagittarius A star was fluctuating rapidly, changing on timescales of minutes rather than years, those changes would be blurred out or missed entirely. Slow processes are easy to document with intermittent observations. Fast ones are not. And black holes, as it turns out, operate on extreme timescales. At the time, however, this possibility remained secondary. The dominant narrative held firm. Sagittarius A star was massive, but calm, powerful, but restrained. An example of what happens when a supermassive black hole runs out of fuel and settles into a low-energy state. This idea wasn't wrong in principle. It was incomplete, because all of it, the low accretion rate, the lack of bright jets, the weak X-ray output, was being interpreted through a narrow observational window. Astronomers were measuring what they could see and building a coherent model around it. The model worked. It explained the data. It fit into broader theories of black hole behavior. What it didn't account for was the possibility that the most important activity around Sagittarius A star was happening in a regime that had never been properly observed. A regime where brightness is subtle, variability is rapid, and energy reveals itself not as a steady glow, but as constant motion. At the time, There was no reason to seriously challenge the quiet black hole label. Every tool available seemed to confirm it. Sagittarius A star appeared to sit at the center of the Milky Way, like a sleeping giant, massive, influential, but largely still. The idea that it might be active in a way no telescope had yet resolved remained unexplored, not because it was unreasonable, but because there was no way to test it. At least, not yet. How our instruments shape the story. For decades, everything we knew about Sagittarius A star was filtered through the capabilities and limitations of our instruments. Every assumption about its quietness, every measurement of low activity was inherently tied to the tools astronomers had at hand. Understanding the black hole, it turned out, required understanding the ways we were blind to it. Ground-based telescopes, even the most advanced, face a fundamental barrier: Earth's atmosphere. Light from space doesn't travel unimpeded to the surface. The air bends it, absorbs it, scatters it. Certain wavelengths, particularly much of the infrared and all far infrared, never reach the ground at all. Even with adaptive optics correcting for turbulence and distortion, these telescopes can only capture a distorted fraction of reality. Early infrared observations could resolve stars near the galactic center, but the black hole itself remained invisible. Its event horizon, its inner accretion flows, the swirling plasma near its edges, all of this lay beyond the reach of those instruments. Astronomers could watch the stars dance around the center, but the stage itself remained unseen. Then there was dust, thick, pervasive and impenetrable to visible light. The Milky Way's central region is a murky tangle of molecular clouds, absorbing and scattering photons before they ever reach us. For years, the densest parts of the galactic center were effectively invisible to optical telescopes. The black hole's own emissions, if they were in these blocked wavelengths, were never detected. What we observed was not what the black hole actually did, but what the universe allowed us to see. Any small bursts, subtle flickers, or fast-moving hot plasma near the event horizon would have been erased from our data simply by intervening material. Even radio observations, which could penetrate some of the dust, had their own limits. Radio telescopes revealed a compact source, the core of Sagittarius A star, but they could not resolve the motion of individual gas clouds or the rapid variations of brightness on short timescales. The black hole appeared as a static dot in the center of the galaxy. Its dynamic life, if it had one, was entirely blurred. Without fine resolution, the assumptions about calmness remained reasonable. What was not visible could not be measured, and what could not be measured could not be accounted for in models. Observation schedules themselves created gaps. Most monitoring campaigns were intermittent, taking data in small windows separated by days, weeks, or months. For slow-moving phenomena, this worked fine. But if Sagittarius A star changed on timescales of minutes or hours, if its plasma flared, cooled, and flared again, these variations would be missed entirely. Instruments captured snapshots of the black hole, not its motion picture. Astronomers could record that it was faint in X-rays today, but what happened between observations was a mystery. The absence of evidence was not evidence of absence. It was evidence of incomplete observation. Even space-based observatories had limitations. Satellites like Chandra and Spitzer could peer into wavelengths blocked by Earth's atmosphere, and they could maintain longer observing campaigns than most ground-based telescopes. Yet they had their own constraints: limited observation time, restricted wavelength ranges, and sensitivity thresholds that filtered out faint or fast-varying signals. Chandra could detect sudden, bright X-ray flares but struggled to capture subtle, continuous flickering. Spitzer could measure infrared light, but it could not resolve minute structures near the event horizon. Every dataset was a compromise, shaped by the instrument's technical boundaries rather than by the black hole itself. All of these constraints combined to create a narrative. Sagittarius. A star was quiet, its feeding was slow, its radiation was weak. It was a black hole in stasis, an anchor at the center of our galaxy rather than an engine. This narrative made sense and fit within theoretical model. For decades, it guided research, influenced simulations, and framed the questions scientists asked. Yet lurking beneath this apparent quietness was the possibility of unseen motion, rapid variations, subtle plasma flows, energy releases invisible in the observed wavelengths. All could have been occurring without leaving a trace in the available data. In effect, our instruments were showing us the calm, but the storm may have already been raging just beyond our vision. The limitations of observation were not failures, they were boundary conditions. Scientists were working with the clearest picture they could assemble, but the universe had a trick. The most important phenomena around Sagittarius A star were happening in a spectrum and on timescales that no one had fully accessed. The black hole's true behaviour was hiding in plain sight, masked by the very filters through which humanity had been peering for decades. It would take a leap in technology, a telescope designed to see through dust, to capture faint infrared light, and to watch the centre of the galaxy continuously to reveal what had been invisible. And that leap would come with the James Webb Space Telescope opening a window onto the Milky Way's core in a way no previous instrument could. How Sagittarius A star compared to other supermassive black holes. While the Milky Way's central black hole remained largely invisible to most instruments, astronomers were busy studying the broader universe, and what they saw painted a striking contrast. Across billions of light years, supermassive black holes revealed themselves in ways that were impossible to miss. Quasars blazed like cosmic lighthouses, their intense radiation outshining entire galaxies. Their presence was dramatic and unmistakable. Jets of plasma shot outward at near-light speeds, glowing in radio, X-ray and optical wavelengths. These black holes devoured massive amounts of matter, converting a substantial fraction of it into energy, creating luminous accretion disks that could be traced across the universe. By comparison, Sagittarius A star seemed almost shy, a silent guardian rather than a raging furnace. This contrast shaped how astronomers framed their understanding. Active black holes, particularly in quasars or galaxies undergoing mergers, were engines of transformation. Their energy output could regulate star formation, heat interstellar gas, and even shape the evolution of the entire host galaxy. When a supermassive black hole consumed gas at high rates, it dominated its surroundings, producing feedback that could ripple across thousands of light years. Sagittarius A star, in contrast, had none of these telltale signatures. Its energy output was minimal, its jets non-existent, its accretion processes barely registering on instruments. To many, this was an archetype of a dormant black hole, massive, gravitationally influential, but otherwise almost invisible. Yet this interpretation had always been conditioned by the tools available. Astronomers could see the dramatic displays of distant quasars because those systems radiated intensely across the electromagnetic spectrum. Their brilliance was impossible to miss. But what about black holes like Sagittarius A star, ones that accreted slowly, emitted faintly, or fluctuated rapidly? Without the right wavelengths and continuous observation, their activity could remain hidden. It wasn't that Sagittarius A star was insignificant, it was that its signature was subtle, and subtle signals are easily lost when compared to the cosmic fireworks of the distant universe. The lack of jets also reinforced the narrative of dormancy. In quasars and other active nuclei, jets serve as a visible indication of matter interacting with powerful magnetic fields near the black hole. They can extend for thousands of light years, shaping galaxies in ways that are readily observable. Sagittarius A star, by contrast, showed no large-scale jets, no extended emissions. It was as if it had the potential for such cosmic drama, but chose restraint instead. For decades, this absence suggested a black hole content to lie quietly, perhaps fed only by sparse stellar winds, rather than massive inflows of gas. Observational comparisons went beyond brightness and jets. Astronomers also looked at the timescales of variability. Active black holes often show fluctuations over days, months, or years, tied to the dynamics of their accretion disks. For Sagittarius A star, the lack of observed flares on these longer timescales seemed to confirm its inactivity. What was not apparent, what instruments could not resolve, was the possibility of faster, smaller-scale fluctuations occurring in minutes or hours. Without a telescope capable of continuous, high-resolution infrared monitoring, these rapid processes would have gone entirely unnoticed. The quiet label became even more entrenched when simulations and models of black hole growth were applied. In theory, low-luminosity supermassive black holes like Sagittarius A star should exist in mature galaxies where gas supply has dwindled. The Milky Way fit this description perfectly. Its central regions are relatively calm compared to starburst galaxies or merging systems. Star formation continues steadily without being disrupted by explosive feedback. The observed low activity of Sagittarius A star aligned with these broader galactic properties, creating a consistent story. The black hole was massive, gravitationally dominant, but effectively dormant. This comparison also shaped expectations for what telescopes might find. If Sagittarius A star behaved like distant quasars, there would be dramatic, detectable signatures. But if it was similar to other low-luminosity black holes in nearby galaxies, then quietness was expected. For decades, the evidence favoured the latter scenario. In the absence of contradictory data, astronomers assumed dormancy. The black hole was treated as a stable anchor, with occasional minor events considered anomalies rather than indicators of continuous activity. Yet lurking in these comparisons was a subtle tension. Sagittarius A star was unique in one crucial way: it was close. While distant supermassive black holes could be observed as bright, single points of light, Sagittarius A star offered the opportunity to resolve its environment at unprecedented detail: the motion of individual stars, the dynamics of accreting material, the influence of gravity on plasma close to the event horizon. The paradox was clear. It appeared quiet because instruments had not fully captured its behavior, but its proximity meant that, with the right tools, the hidden activity could finally be revealed. This tension between apparent dormancy and potential dynamism set the stage for the next revolution in observation. Astronomers had long accepted Sagittarius A star as a quiet supermassive black hole, distinct from its brilliant cousins in distant galaxies. They had built models, simulations, and expectations based on decades of imperfect data. Yet the black hole's true nature remained concealed, waiting for a telescope that could pierce the dust, observe continuously, and detect faint and fast varying signals. The quiet narrative had dominated scientific thinking for decades, reinforced by comparisons with other black holes, by apparent inactivity in all measured wavelengths, and by models consistent with a mature galaxy's central engine. But all of it depended on the limits of observation. And as history would soon show, those limits were not the black hole's reality. They were simply the edge of human vision. But the tools that had shaped this understanding were about to be surpassed. And with that leap, everything we thought we knew about our galaxy's central black hole would begin to change. JWST's infrared advantage: seeing the unseen. For decades, astronomers had struggled to understand Sagittarius A star, the supermassive black hole at the heart of the Milky Way. Every telescope, every observation, every painstaking measurement seemed to tell the same story. It was quiet, dormant, almost invisible. Yet there was a nagging sense that this was not the whole truth. The problem was not the black hole itself. The problem was our view of it. Dust, gas, and distance had conspired to hide the central engine from our eyes. What humans needed was a telescope that could not only pierce the murky veil of the galactic center, but also detect the faint energy that had been eluding instruments for decades. That telescope would be the James Webb Space Telescope, or JWST. What made Webb revolutionary was its ability to see in infrared. Infrared light is not the same as the visible light our eyes detect. Instead of focusing on what we can see, Infrared detects heat, the energy emitted by objects as they warm their surroundings. For stars and galaxies, this opens a window into regions that are hidden in visible light. For Sagittarius A star, infrared was a game changer. Dense molecular clouds and interstellar dust that block optical light are largely transparent to infrared wavelengths. Where previous telescopes had seen nothing but dark obscurity, Webb could see glowing structures and dynamic processes that had remained entirely invisible. The advantage of infrared is particularly crucial at the centre of the Milky Way. The galactic plane is crowded with stars, gas clouds and cosmic dust. As light travels through this environment, it is absorbed, scattered, and sometimes completely extinguished. Visible light cannot penetrate these regions, leaving astronomers with a distorted or entirely blocked picture. Infrared, however, can slip through these barriers. By detecting the heat emitted by matter near the black hole, infrared imaging allows scientists to map the motion, distribution, and energy of material that was previously hidden. Suddenly, the central parsecs of the galaxy, once shrouded in near-total darkness, could be studied in unprecedented detail. Webb is equipped with two instruments that were particularly vital for studying Sagittarius A star. The first is NIRCam, the near-infrared camera. NIRCam operates in wavelengths just beyond what humans can see, capturing light emitted by hot stars and warm dust. This makes it ideal for resolving individual stars near the galactic center and for detecting the faint glow of material heated as it spirals toward the black hole. NIRCam's sensitivity allows it to detect subtle variations in brightness and structure, revealing patterns that would be invisible to optical or even ground-based infrared telescopes. The second instrument is MIRI, the mid-infrared instrument. MIRI observes at longer wavelengths than NIRCam, targeting the heat emitted by cooler dust and gas. This allows it to map regions further from the hottest stars while still penetrating the galactic dust. MIRI can detect thermal emissions from material heated indirectly by the black hole or by nearby stars. Together, NIRCam and MIRI create a multi-layered view. NIRCam captures the hottest, most immediate structures near Sagittarius A star, while MIRI provides context by mapping the surrounding environment. This combination makes it possible not just to locate the black hole's surroundings, but to study how matter flows and interacts with it. Infrared also allows astronomers to detect variability in the black hole's behavior. Previously, instruments were limited to snapshots, catching only a few hours or minutes of activity at a time. With infrared, Webb can detect subtle changes in heat emitted by material near the event horizon. This means that what once appeared static or dormant can now be observed in motion. Fluctuations in brightness, previously invisible, become signals of underlying activity, the turbulent dance of hot plasma, magnetic reconnections, or matter inching ever closer to the point of no return. This sensitivity to heat rather than light is what makes Webb transformative. The black hole at the center of our galaxy is not an empty void. Matter swirls, magnetic fields twist, and energy is released in ways that are not visible in optical light. Infrared does not care about dust or scattering. It records the energy emitted by these processes. For the first time, astronomers could see the dynamics of the galactic center in real time, without the blind spots that had hindered previous studies. Webb's infrared advantage also allows astronomers to detect extreme environments that were previously inaccessible. Hot gas orbiting near the event horizon emits strongly in the infrared, and even small amounts of material moving at relativistic speeds produce measurable heat signatures. With NIRCam and MIRI, scientists can track these motions, map the distribution of hot plasma, and even infer the structure of magnetic fields influencing the matter near the black hole. In effect, infrared transforms an invisible, silent object into a living, observable system. Finally, the infrared capabilities of Webb are not just about detection, they are about resolution and clarity. Previous instruments, whether on the ground or in space, could see the galactic center as a fuzzy blur, unable to distinguish the fine structures near the black hole. Webb's instruments can resolve individual stars and gas streams, detect brightness fluctuations on small scales, and differentiate overlapping structures that were previously indistinguishable. This precision is essential for understanding not just what Sagittarius A star is, but how it interacts with its environment. JWST's infrared vision is not a minor upgrade over past telescopes. It is a fundamental redefinition of what is observable. Dust that once obscured the galactic core is now transparent. Material too faint or too fleeting to detect becomes visible. Hot plasma, swirling gas, and magnetic activity can finally be studied in detail. NIRCam and MIRI together provide a multi-dimensional view, capturing both the immediate environment of the black hole and the surrounding context of the central galaxy. Why space matters. Seeing without Earth in the way. When astronomers first trained telescopes on the heart of the Milky Way, they faced a challenge that was as much about Earth as it was about the galaxy itself. No matter how advanced the instruments, no matter how ingenious the techniques, there was one fundamental obstacle: our planet. The atmosphere that sustains life on Earth also distorts, absorbs, and filters the light coming from space. It is a blessing for life, but a curse for astronomy. To truly see Sagittarius A star, to witness the motions of hot plasma, the flickering of accretion flows, the twists of magnetic fields near a supermassive black hole, scientists needed to rise above the atmosphere entirely. They needed to leave Earth behind. From the surface, the atmosphere imposes three major limits. First, it absorbs specific wavelengths of light. While visible light largely makes it through, much of the infrared, ultraviolet, and far infrared radiation is blocked entirely. For the Milky Way's central black hole, this is catastrophic. The densest regions of dust and gas surrounding Sagittarius A star emit strongly in infrared, yet the lower layers of Earth's atmosphere absorb or scatter that light. Instruments on the ground are blind to entire swaths of information, forcing astronomers to infer activity indirectly or wait for rare atmospheric windows to open. Second, the atmosphere introduces turbulence. Even on clear nights, air currents bend and distort incoming light, a phenomenon known as atmospheric seeing. Stars twinkle because of this effect. For telescopes aiming at the galactic center, turbulence blurs the fine details. Adaptive optics can correct for some of this distortion, but only partially, and only in narrow fields of view. Rapid changes in the atmosphere mean that some light never reaches the detector in a coherent form, erasing subtle variations that could indicate activity near the black hole. Third, the atmosphere contributes background noise. Air molecules, water vapor, and temperature gradients all emit radiation that interferes with faint signals from space. This makes detecting delicate infrared emissions incredibly difficult. The faint flicker of hot plasma near Sagittarius A star could be drowned out in a background of terrestrial heat and scattered light. For decades, astronomers were trying to hear a whisper through a hurricane. The black hole might have been communicating, but the instruments on Earth were never quite sensitive enough to catch it. This is where space-based observatories change everything. By placing a telescope like JWST at a location beyond the atmosphere, astronomers remove all of these constraints. Infrared light that would be absorbed by air now reaches the telescope unimpeded. Turbulence is eliminated, allowing the instruments to record images with unprecedented clarity. Background noise from the planet disappears, revealing faint structures and subtle motions that ground-based observatories could only hint at. For Sagittarius A star, this is not just an incremental improvement, it is a revolution. Suddenly, a region that once seemed quiet and uneventful bursts into detail. Streams of hot plasma, previously invisible, become detectable. The flicker of matter approaching the event horizon can be observed directly. Magnetic activity, accretion flows and energetic variations no longer remain theoretical. They can be measured. But escaping the atmosphere is only part of the story. Space also offers freedom in time. From the ground, observation windows are limited by day-night cycles, weather conditions, and seasonal positioning of the galactic center. Most observatories can only observe Sagittarius A star for a few hours per night, with interruptions from clouds, humidity, and other environmental factors. Continuous monitoring is nearly impossible. For phenomena that occur on short timescales, minutes, hours, even seconds, this is devastating. A flare of hot plasma near the event horizon could erupt and vanish in a single night, leaving no trace for ground-based instruments to capture. JWST solves this problem through its orbit at L2, the second Lagrange point, roughly 1.5 million kilometers from Earth. There, the telescope has a stable environment, far from the planet's day-night cycles, weather, and heat emissions. It can point at the galactic center for long, uninterrupted periods. Continuous monitoring over hours, days, and even weeks becomes possible, capturing variations in brightness and motion that were previously invisible. For the first time, astronomers could record Sagittarius A star in action, not as a series of isolated snapshots, but as a continuous live performance. Another advantage of space is thermal stability. On Earth, temperatures fluctuate, causing small expansions and contractions in telescope components. This affects calibration, introduces noise, and reduces precision. In space, JWST's instruments operate in a thermally controlled environment, cooled to near absolute zero. Infrared detectors are extremely sensitive to heat. Any background thermal emission can overwhelm the faint cosmic signals. By placing JWST in deep space and shielding it from sunlight and Earth's heat, engineers created conditions where the faintest infrared emissions from Sagittarius A star could be recorded reliably. This level of stability is essential to detect subtle variations in the black hole's accretion flows and magnetic fields. The location in space also allows JWST to observe multiple wavelengths simultaneously without interference. On the ground, instruments must contend with atmospheric absorption that varies with wavelength. Some parts of the infrared spectrum never reach Earth at all, and others fluctuate depending on weather and humidity. In space, all wavelengths within the telescope's design reach the detectors cleanly. NIRCam and MIRI can operate in parallel, capturing near and mid-infrared light at the same time. This simultaneous imaging allows scientists to correlate activity across wavelengths, revealing patterns and interactions that would be invisible with sequential observations from ground-based telescopes. This combination of infrared capability, freedom from atmospheric distortion, and thermal stability fundamentally changes what is observable. Sagittarius A star, previously labelled quiet, is no longer constrained by human limitations. The structures near the event horizon, the flow of hot gas, the twisting magnetic fields all become accessible for study. A system that seemed dormant when observed from Earth now reveals itself as dynamic, with subtle energy releases and motions occurring on timescales that were previously undetectable. Space also allows for precision in timing. JWST can monitor changes in brightness, temperature, and movement, with exacting temporal resolution. This is critical for understanding a black hole because the region near the event horizon operates on extreme scales. Matter can orbit the black hole in mere minutes, plasma can flare unpredictably, and magnetic fields can reconfigure rapidly. Capturing these events requires continuous, uninterrupted observation, something only possible when freed from Earth cycles. Furthermore, JWST's location enables collaboration with other space-based observatories. By combining infrared data from JWST with X-ray observations from Chandra, Radio data from space-based interferometers and gamma-ray measurements from orbiting instruments, scientists can construct a multi-dimensional, multi-wavelength view of Sagittarius A star. No single Earth-based telescope could provide such comprehensive coverage. Space-based observation creates a unified platform to capture a black hole's behavior across the spectrum. For Sagittarius A star, the importance of space cannot be overstated. For decades, astronomers had inferred inactivity based on what could be measured from Earth. Every observation was limited by the planet itself, the atmosphere, turbulence, background noise, and time constraints. These limitations created a narrative of dormancy. Space removes those limitations entirely. It allows scientists to see directly, continuously, and comprehensively. With JWST, the Milky Way's supermassive black hole is no longer a distant, static object. It can be observed dynamically, in detail, and in real time. Heat, motion, and magnetic interactions become measurable phenomena. Continuous, high-resolution, multi-wavelength monitoring becomes possible. For the first time, humans can watch Sagittarius A star live, capturing the matter and energy that defines a supermassive black hole. Space transforms the question from what is happening at the center of our galaxy to how is it happening moment by moment. The galaxy's heart, once hidden behind layers of dust and atmosphere, is now fully accessible. JWST's vantage point, far from Earth, free of interference and optimized for infrared observation, allows scientists to study the black hole as a living system with dynamic processes that were previously invisible or misunderstood. Observation strategy: watching the black hole live. Observing a supermassive black hole is nothing like pointing a camera at a distant star. It's not a simple snapshot. It requires patience, precision, and a strategy built around understanding extreme physics and the limits of human instruments. James Webb Space Telescope didn't just aim at Sagittarius A star once and hope to catch something interesting. The scientists behind it designed a careful observation plan, one that allowed the black hole to reveal itself continuously, dynamically, and across multiple layers of reality. For the first time, they were not taking fragments of information. They were watching a cosmic process unfold in real time. The foundation of this strategy was long, uninterrupted monitoring. Unlike ground-based telescopes, which are constrained by the day-night cycle, weather, and atmospheric conditions, Webb could stare at the galactic center for hours, sometimes even days, without interruption. This continuous gaze is essential for catching events that occur on short timescales. Matter orbiting close to the event horizon moves fast, completing orbits in mere minutes. Magnetic reconnections, flares, and turbulence in the accretion disk can rise and fall in the same timescale. To understand these fleeting phenomena, astronomers needed a telescope that could collect data continuously, recording every fluctuation as it happened. Webb's strategy was to schedule long observation periods, allowing it to capture the rise and fall of activity without missing a single beat. Simultaneous multi-wavelength imaging was another critical aspect of the observation plan. Sagittarius A star emits energy across the spectrum, from infrared to X-rays and beyond. Different processes manifest at different wavelengths. Hot plasma near the event horizon glows in near-infrared, while cooler dust farther out emits primarily in mid-infrared. By using NIRCam and MIRI together, scientists could observe both short and long wavelength emissions at the same time. This approach allowed them to connect events. A flare detected in near-infrared could be traced to structures in mid-infrared, revealing how matter moved, heated, and interacted over space and time. Observing multiple wavelengths simultaneously turns a static picture into a dynamic map, showing how energy flows through the environment of the black hole. Timing was everything. With continuous observations and multiple wavelengths, astronomers could track variability in brightness and motion, with precision down to minutes. This level of temporal resolution is critical because the physics near a supermassive black hole is extreme. Gas and dust move at relativistic speeds. Gravitational forces bend light. Magnetic fields twist and snap in unpredictable ways. Capturing these events requires not just high-resolution imaging, but also a consistent, uninterrupted time series of data. Webb's observation strategy accounted for this by keeping its instruments focused on the galactic center for extended periods, ensuring that even the fastest events would be recorded. Another element of the strategy was the careful calibration and alignment of instruments. Observing a black hole is not just about pointing a telescope, it's about ensuring that every photon is correctly recorded and matched across different detectors. NARCAM and MAIRI are sensitive to slightly different regions of the spectrum, and their images must be carefully synchronized. Webb's engineers designed observation sequences that allowed simultaneous exposure while correcting for tiny differences in detector response, cosmic ray interference, and thermal variations. The result is data that is clean, coherent, and ready for analysis, capturing every nuance of the black hole's behavior. The strategy also included monitoring not just the black hole itself, but its environment. Sagittarius A star is not alone. It is surrounded by a dense cluster of stars, streams of gas, and clouds of dust. These neighbouring objects influence the black hole's behaviour, feeding it matter, interacting with magnetic fields, and sometimes triggering small flares. By including these surrounding regions in the observation field, scientists could study how matter travels inward toward the event horizon, how stellar winds contribute to accretion, and how the environment as a whole responds to the black hole's gravity. This contextual approach ensures that every observation captures not just isolated events, but the interconnected dynamics of the galactic center. JWST's observation strategy also considered variability over longer timescales. While rapid flares happen in minutes, other processes take hours, days, or even weeks. By scheduling repeated observation sessions, astronomers could capture patterns and cycles, linking short-term variability to longer-term trends. This strategy creates a multi-layered understanding of activity, showing not just isolated events, but the rhythm and structure of the black hole's behavior over time. Importantly, the strategy was designed with a focus on precision rather than volume. It is tempting to collect as many images as possible, but for a target as challenging as Sagittarius A star, data quality matters more than quantity. Webb's team prioritized carefully planned, high-resolution observations over rapid-fire imaging. This allowed the instruments to gather maximum detail, reduce noise, and produce images where subtle changes in brightness and motion could be confidently interpreted. Every hour of observation was optimized to reveal the most about the black hole's dynamics, rather than simply accumulating more data. The observation plan also relied on coordination with other observatories. Although JWST provided unprecedented infrared capability, understanding Sagittarius A star fully requires multi-wavelength perspectives. X-ray data from Chandra, radio observations from arrays like ALMA, and even occasional optical monitoring combine with Webb's infrared images to create a comprehensive view of the black hole and its environment. The observation strategy accounted for this by scheduling sessions to overlap with these other instruments when possible, creating a coordinated, multi-dimensional approach to monitoring. The final aspect of the strategy was flexibility. Black holes are unpredictable. A sudden flare or unexpected behavior could occur at any time. JWST's observation plan included the ability to adjust targets and exposure sequences in response to new events. This responsiveness allows scientists to capture rare or unusual phenomena as they happen, ensuring that nothing is missed. It transforms the telescope from a passive observer into an active participant in real-time discovery, ready to capture whatever the universe reveals. All of these components together, long uninterrupted monitoring, simultaneous multi-wavelength imaging, careful calibration, environmental context, coordination with other observatories, and operational flexibility define Webb's observation strategy. They allow the telescope to move beyond snapshots and instead record the black hole as it lives and breathes, with every flicker of energy, every swirl of matter, and every twist of magnetic fields. For the first time, Sagittarius A star could be observed as a dynamic system rather than a quiet dot on a map. What had once appeared dormant could now be studied in motion. Its accretion flows, plasma flares, and surrounding environment became measurable, trackable, and interpretable. The black hole was no longer an abstraction. It was a living, evolving system, observed with a precision and continuity never before possible. This observation strategy set the stage for discoveries that would challenge decades of assumptions about our galaxy's central black hole. What Webb was specifically looking for. James Webb wasn't simply pointing its cameras at Sagittarius A star without a plan. Every observation was designed to target the most critical and dynamic phenomena near the black hole. The team focused on 4 key aspects of black hole physics: the behavior of the accretion disk, the movement of hot plasma near the event horizon, magnetic activity, and the interplay between short and long wavelength emissions. Each of these areas held clues to understanding why Sagittarius A star appeared quiet from Earth and what processes were actually occurring just beyond our sight. The accretion disk is the first target. Surrounding the event horizon, it consists of gas and dust spiraling inward under immense gravitational forces. In other supermassive black holes, these disks often glow brightly across the electromagnetic spectrum, but in Sagittarius A star, they seemed faint or invisible in previous observations. Webb's infrared instruments can detect the heat emitted by material in these disks. This allows scientists to map its density, structure, and dynamics. Small fluctuations in brightness reveal how matter moves closer to the black hole, how it heats up, and how energy is released as it interacts with intense gravity. Observing the accretion disk in near and mid-infrared simultaneously enables researchers to distinguish the hottest material near the horizon from cooler layers further out, giving a layered view of its motion and energy output. Hot plasma near the event horizon was another critical focus. Matter approaching the point of no return can reach millions of degrees, producing energy across multiple wavelengths. Previous telescopes could detect only the brightest flares in X-ray or radio, missing subtler, continuous activity. Webb can capture the infrared glow of this plasma as it twists, collides, and accelerates around the black hole. Scientists can measure the plasma's temperature, density, and velocity, tracking the material as it spirals inward and interacts with the black hole's gravity. This provides insight into the feeding process of the black hole and the dynamics in the innermost stable orbit, where gravity and relativistic effects dominate. Magnetic activity is also central to understanding Sagittarius A star. Magnetic fields can twist and reconnect, creating sudden bursts of energy and shaping the motion of plasma in the accretion disk. These fields are invisible in traditional optical or radio imaging, but their effects heat surrounding matter, producing detectable infrared emissions. By observing variations in brightness and motion over time, Webb can infer the strength and orientation of magnetic fields. This is crucial for explaining phenomena such as localized flares, sudden changes in disk structure, or energy transport near the event horizon. Mapping magnetic activity allows astronomers to connect the movement of plasma with underlying forces that govern the black hole's behavior. Finally, Webb focused on linking short and long wavelength emissions. NARCAM captures near-infrared, revealing hot, fast-moving material close to the black hole, while MARI detects mid-infrared, mapping cooler dust and gas further out. Observing both at the same time provides a dynamic map showing how energy propagates through the environment. A flare in near-infrared can be traced to heating of surrounding dust in mid-infrared, showing the interaction between immediate black hole activity and its broader surroundings. This simultaneous imaging allows scientists to understand cause and effect in the galactic center, rather than relying on isolated snapshots of events. The observation sequences were designed for multi-hour continuous monitoring. Each session captures minute-by-minute changes in brightness, structure, and motion. This level of temporal resolution allows researchers to see rapid flares, plasma swirls, and fluctuations in the accretion disk that were invisible in previous data. Webb's strategy ensures that nothing in the immediate environment goes unnoticed, recording both subtle and dramatic phenomena with high precision. With these instruments and this approach, scientists could finally answer questions that had lingered for decades. How does matter behave as it approaches Sagittarius A star? What is the structure of its accretion disk? How does magnetic energy influence plasma near the horizon? How do emissions at different wavelengths connect? And what does that reveal about the black hole's activity? Webb's observations were built to capture these dynamics directly, revealing processes that had been invisible to every telescope before. Every measurement, exposure, and sequence was crafted to translate the invisible into the observable. Near-infrared captures the immediate environment. Mid-infrared contextualizes it within the surrounding galactic center. The observation that changed everything. The observation campaign started with a precise schedule, weeks of continuous monitoring aimed squarely at the center of the Milky Way. Every orbit, every exposure, every second was planned to catch activity near Sagittarius A star. For years, astronomers had relied on scattered snapshots from different telescopes, each giving only a fragment of the story. With the campaign underway, the black hole finally revealed a rhythm that had never been recorded. Almost immediately, flickering appeared in the data. It was subtle at first, a small rise and fall in brightness, barely noticeable compared to the vast darkness around it. But it was relentless. Minute by minute, the light shifted, fluctuating across the near-infrared and mid-infrared bands. Smaller variations repeated every few minutes, like ripples in a cosmic pond. Over the course of hours, these flickers grew into full flares, bright surges that spiked dramatically before fading again. The pattern was unmistakable. Bright flares erupted every few hours, dominating the light from the region, while smaller fluctuations persisted between them. Nothing about this had been anticipated. Models had predicted calmness, near dormancy, a quiet supermassive black hole with only occasional activity. Yet here was a black hole that refused to remain quiet. Its environment pulsed with energy, never fully still, always churning. Every flare and flicker came from incredibly close to the event horizon, within the innermost reaches of the black hole's gravitational influence. This proximity meant the light observed was tied directly to processes occurring in the region where gravity is extreme and relativistic effects are dominant. The smallest changes in brightness reflected movements of matter just outside the point of no return. Plasma heated to millions of degrees as it swirled around the event horizon. The observations captured variability across multiple wavelengths. Near-infrared revealed the hottest, fastest moving plasma, while mid-infrared recorded slightly cooler material in the surrounding accretion flows. The two instruments often showed correlated changes, with short wavelength peaks appearing first, followed by lagging longer wavelength signals. Each flare, each flicker, traced the flow of energy through the immediate environment of the black hole. Minute-by-minute tracking revealed unexpected complexity. Fluctuations weren't uniform. Some regions brightened while neighboring areas dimmed. Plasma streams twisted in patterns that suggested strong, fluctuating magnetic fields. Hot clumps appeared to move along arcs around the event horizon, accelerating and decelerating in irregular bursts. This level of detail had never been observed in Sagittarius A star before. It was no longer a static object. It was dynamic, restless, and unpredictable. Flares reached brightness levels that dwarfed anything detected in prior infrared campaigns. Even mid-infrared light, which traces cooler material, showed marked variations, suggesting that energy released near the event horizon propagated outward, heating surrounding gas and dust. This cascading effect indicated an environment in constant motion, with energy travelling through different layers of matter, affecting both immediate and nearby regions. The campaign recorded smaller fluctuations on timescales of mere minutes, rapid rises and falls that could easily have been missed with shorter observations. These short-term variations reflected processes occurring extremely close to the black hole, including turbulence in the inner accretion disk and interactions between plasma and magnetic fields. The precision of these measurements allowed astronomers to separate different types of variability, distinguishing local, rapid processes from larger, slower flares. In parallel, the data showed consistency over hours and days. Flares repeated in patterns that suggested the black hole was continuously active rather than sporadically erupting. Each flare, each pulse, added to the understanding of the environment near the event horizon, revealing a cycle of energy release and dissipation. Patterns emerged that pointed to rotating plasma streams, localized heating, and intermittent magnetic reconnection events. The campaign also revealed spatial structure. Different regions around the black hole exhibited variability at slightly different times and wavelengths. Bright knots of plasma appeared to orbit the event horizon, moving along arcs visible in near-infrared. Cooler material in mid-infrared responded to these movements with slight delays, reflecting the spread of energy outward from the hottest, innermost regions. Every new observation contradicted the notion that Sagittarius A star was dormant. It was not a silent anchor at the galaxy's center. It was a churning engine, a system alive with energy, plasma, and magnetic activity. Minute by minute, hour by hour, the black hole displayed an unexpected complexity, a dynamic environment shaped by forces that could now be observed directly. These measurements captured the extremes of the black hole's influence. Bright flares originated within a few million kilometers of the event horizon, an area so compact that the motion of plasma could be measured in real time. Smaller fluctuations traced the behavior of individual streams of matter as they accelerated, heated, and interacted with magnetic fields. Each pulse of light was a direct signature of processes occurring in a region where gravity and energy densities reach extremes unmatched anywhere else in the Milky Way. Simultaneous observations across short and long wavelengths provided insight into the timing of these events. Peaks in near-infrared often preceded increases in mid-infrared by several minutes, revealing the movement of energy outward from the inner accretion disk. This lag in timing offered clues about how matter is heated, how energy propagates, and how different layers of the black hole's environment interact. The campaign revealed repeated cycles. Bright flares every few hours were punctuated by rapid, minute-scale flickers. Long sequences of data allowed astronomers to track these patterns over days, comparing how flares differed in strength, duration, and wavelength response. Some flares rose gradually and decayed slowly, while others erupted violently and faded within minutes. The variability itself became a source of information, offering insight into the physical conditions near the event horizon. Overall, the observation campaign provided a continuous, multi-dimensional record of Sagittarius A star. Minute-scale fluctuations, hour-scale flares, short and long wavelength timing differences, and spatial variation combined into a single, detailed picture of a black hole environment in constant motion. Every photon recorded added to an understanding of how matter, energy, and magnetic fields interact in a region of extreme gravity. This detailed timeline revealed that Sagittarius A star was far from inert. Minute by minute, hour by hour, the black hole's activity was recorded in exquisite detail, showing not only flares and flickers, but also the underlying structures and motions producing them. The emissions originated from regions within a few million kilometers of the event horizon, where gravity, heat, and magnetism combined to create a turbulent, energetic system. The observation campaign turned a theoretical understanding of a quiet black hole into direct evidence of dynamic activity. Continuous monitoring across multiple wavelengths produced a record of variability that had never been captured before. Fluctuations on minute scales, repeated flares over hours, and coordinated timing between near and mid-infrared revealed processes that were entirely invisible to previous instruments. Sagittarius A star was a system defined by movement, energy, and complexity, with emissions rising, falling, and shifting across multiple regions near the event horizon. Minute by minute, the environment was alive with flares, plasma streams, and magnetic interactions, producing patterns of variability showed constant activity. The variability that stunned scientists. As the data streamed in from the observation campaign, scientists began to notice patterns that challenged every assumption about Sagittarius A star. The black hole wasn't merely flickering, it was fluctuating in ways that models had never predicted. Every few hours, bright flares erupted from the immediate vicinity of the event horizon, erupting and fading in cycles that repeated over the observation period. These flares were interspersed with smaller, faster fluctuations every few minutes, forming a constant backdrop of dynamic energy. What made this remarkable was not just the presence of activity, but the scale, speed, and unpredictability of these variations. Short wavelength emissions captured by NIRCam consistently led the action. Bright spikes in near-infrared appeared first, concentrated in the hottest regions closest to the event horizon. These bursts often reach several times the baseline brightness, showing the rapid release of energy from accelerated plasma. Mid-infrared emissions, recorded by Murray, reacted differently. They lagged behind the near-infrared peaks by several minutes, gradually brightening as energy propagated outward from the inner accretion disk. This clear separation in timing between wavelengths provided a direct measure of how energy moves through the environment around the black hole, revealing interactions that had never been directly observed before. The rapid variability at short wavelengths was a constant source of surprise. Minute-scale flickers indicated that plasma was being accelerated, heated, and cooled in bursts rather than a continuous flow. These microfluctuations hinted at processes occurring just above the event horizon, where gravity bends light and relativistic speeds dominate the motion of matter. The observation showed arcs of plasma twisting, brightening, and fading in ways that suggested strong, dynamic magnetic fields threading the inner accretion disk. Longer wavelength emissions, although slower to respond, provided critical context. The delayed rise of mid-infrared brightness traced the spread of heat into surrounding dust and gas. It revealed that energy from the inner disk did not simply vanish, it travelled outward, influencing the environment across a larger scale. Scientists could measure the lag in brightness precisely, which allowed them to infer the density and composition of surrounding material, as well as the mechanisms by which energy was dissipated. The combination of rapid near-infrared flares and delayed mid-infrared responses exposed a level of complexity that no one had anticipated. Previous models assumed that Sagittarius A star was largely inactive, with occasional minor flares. Instead, the black hole exhibited continuous activity on multiple timescales, driven by processes occurring just above the event horizon. Plasma accelerated in bursts, magnetic reconnections released energy unpredictably, and the surrounding environment responded in a coordinated yet delayed manner. One particularly striking observation was the pattern of short and long wavelength emissions during consecutive flares. Some flares were sharp and intense, with near-infrared peaks rising and falling within minutes, while others were broader, slower, and more sustained. Mid-infrared responses mirrored this variability, but with consistent lag times. This showed that the black hole's output was not uniform. It varied in intensity, duration, and structure, revealing a system that is constantly in motion, yet governed by underlying physical processes. The level of variability was unprecedented. Minute-to-minute fluctuation suggested that the accretion disk was not a smooth, continuous structure. Instead, it was turbulent, with clumps of matter interacting, colliding, and accelerating at different speeds. Bright knots of plasma would brighten briefly before fading, sometimes merging with neighbouring clumps or dissipating entirely. Magnetic activity appeared to govern these motions, creating unpredictable bursts of energy that dominated the near-infrared signal. Scientists also noticed that flares were not isolated events. Energy released from one flare appeared to influence subsequent activity. A bright near-infrared flare could trigger a series of smaller fluctuations as plasma streams shifted or magnetic fields reconfigured. Mid-infrared emissions traced these energy transfers, lagging behind but recording the movement of heat and charged particles through surrounding matter. This interplay between wavelengths revealed the black hole as a highly interconnected system, where activity at the event horizon rippled outward into the surrounding environment. The continuous observation campaign allowed astronomers to measure the frequency and scale of flares with precision. Bright flares recurred roughly every few hours, creating a semi-regular pattern, while smaller fluctuations occurred almost continuously on minute scales. This range of variability showed that Sagittarius A star operates across multiple timescales simultaneously, with processes in the inner disk influencing and feeding into broader activity in the surrounding regions. Short wavelength flares often rose faster than they decayed, indicating rapid heating of plasma followed by slower cooling. Mid-infrared responses rose more gradually and decayed at a similar pace, showing the diffusion of energy into cooler material. Timing differences were consistent across multiple flares, suggesting a reproducible mechanism by which energy is released and propagated. This timing allowed scientists to model the acceleration of particles and the movement of heat across the accretion disk and into the surrounding dust clouds. The scale of variability extended beyond the immediate inner disk. Observations showed that material several light minutes from the event horizon responded to changes at the center, brightening and dimming as energy propagated outward. This revealed the size of the region influenced by the black hole's activity, showing how far the effects of rapid plasma heating and magnetic reconnections could reach. The combination of continuous monitoring, multi-wavelength timing, and spatial resolution produced a dynamic, multi-layered map of Sagittarius A star. Each flare and flicker became a piece of evidence for the physics at work near the black hole. Plasma streams, magnetic loops, and energy propagation were no longer theoretical constructs. They were recorded, measurable events. Minute-by-minute variability showed how plasma was accelerated near the event horizon. Hour-scale flares revealed the broader dynamics of accretion and energy transfer. Wavelength-dependent timing traced energy movement from the hottest inner regions to cooler surrounding material. All of these observations highlighted an environment of constant motion, where flares, plasma streams, and magnetic reconnections interact across multiple scales. Every sequence captured new detail, knots of plasma twisting and brightening, flares erupting unpredictably, mid-infrared emissions lagging behind near-infrared peaks, and energy spreading into surrounding gas and dust. The data revealed that Sagittarius A star operates across timescales, wavelengths, and spatial scales simultaneously, with rapid changes near the event horizon producing cascading effects outward. The observation campaign showed that variability is not random noise. It is structured, energetic, and directly tied to physical processes in the black hole's immediate environment. Minute to minute flickers and hour-scale flares are signatures of particle acceleration, turbulent plasma, and magnetic interactions. Short and long wavelength timing provides a detailed chronology of how energy moves from the inner accretion disk into the surrounding material. The patterns observed contradicted previous expectations of a dormant black hole. Sagittarius A star exhibits variability on multiple timescales, with energy release occurring continuously in small bursts, punctuated by larger flares. Its emissions are structured and wavelength dependent, reflecting a complex interplay of gravity, plasma motion, and magnetism. The shocking physics of Sagittarius. A star. Sagittarius, a star isn't quiet. The flickers, the flares, the constant changes, everything is happening at lightning speed in a place where gravity crushes, heat burns, and magnetic fields twist violently. Near-infrared light pulses first, erupting in sudden spikes of brightness. Minutes later, mid-infrared light catches up, glowing as the heat spreads outward. Every flare is a heartbeat, every flicker a signal from the edge of the black hole itself. The inner edge of the accretion disk is a storm. Streams of plasma swirl, twist, and collide, moving so fast that time seems almost different. Particles accelerate along invisible, magnetic lines, flinging through space at near light speed. The brightest bursts come from these supercharged particles releasing energy in a brilliant near-infrared flare, a kind of cosmic firework. Then the surrounding cooler gas and dust heat up, sending out mid-infrared light, a delayed echo of the original explosion. Minute-to-minute flickers reveal turbulence on a scale almost impossible to imagine. Tiny clumps of matter collide, merge, or get torn apart. Magnetic fields snap and reconnect, releasing sudden bursts of energy. Some flares explode violently, others rise slowly and fade gently, painting a complex and unpredictable rhythm across the black hole's surroundings. Energy moves outward in waves. A flare close to the event horizon doesn't stay put. It spreads, travelling through the swirling disk, heating nearby gas, nudging dust clouds, and creating ripples of light across the galactic centre. The delay between near-infrared and mid-infrared emissions shows exactly how fast this energy moves. It's a clockwork of heat and light, revealing the invisible forces shaping the environment around the black hole. The light itself tells a story. Sharp near-infrared spikes track the hottest, fastest moving plasma. Slower mid-infrared glows map the cooler surroundings, tracing the path of energy as it moves outward. Each flare, each pulse, is a record of acceleration, turbulence, and magnetic tension. The black hole's environment is alive, constantly energized, constantly changing. Even the smallest flickers have meaning. Rapid rises and falls in brightness hint at plasma colliding at relativistic speeds, magnetic loops snapping, and sudden bursts of energy shooting outward. Minute-scale activity is layered on top of larger, hour-long flares, creating a multi-scale dance of light and motion. It's chaos, but it has structure, a rhythm hidden in the violence of extreme gravity. The timing of the flares is like a cosmic clock. Short wavelength bursts spike first, then longer wavelength responses follow. This shows energy travelling from the hottest regions near the event horizon into cooler areas nearby. It's a direct glimpse into the physics at play. Particles are accelerated, heated, and cooled, and magnetic fields control the motion of everything around them. Sagittarius A star is less like a dormant black hole and more like a machine in constant motion. Matter swirls in, flares erupt unpredictably, energy pulses outward, and magnetic forces twist everything in a chaotic, mesmerizing pattern. Minute flickers, hour-long flares, and wavelength delays all combine to reveal a black hole that is endlessly active, its environment alive with motion, energy, and light. Accretion, Disk Basics. At the center of the Milky Way, a black hole lies in a region of space that is anything but empty, surrounding Sagittarius. A star is a disk of plasma so hot and dense that temperatures reach millions of degrees. This accretion disk is not a smooth, calm ring. It is a chaotic swirl of material moving at nearly the speed of light. Each particle orbits the black hole under the grip of extreme gravity, circling faster the closer it gets. The innermost regions just outside the event horizon are packed with plasma accelerating so rapidly that relativistic effects become significant. Time, light, and motion all bend under the intense gravity. The disk is fed continuously by streams of gas and dust from nearby stars, as well as leftover material from the galaxy's formation. As this material spirals inward, friction and compression heat it to extraordinary temperatures. Hot plasma radiates energy, but not evenly. Some regions flare suddenly, while neighboring areas remain comparatively dim. These fluctuations are the first sign of an intricate network of forces at work: gravity, pressure, and magnetism interacting in extreme conditions. One of the most important processes in the accretion disk is magnetic reconnection. Magnetic fields thread the plasma in loops and arcs, carrying energy and tension. When these twisted fields snap or realign, they release enormous amounts of energy almost instantaneously. This process is similar to what happens in solar flares on the Sun, but scaled up millions of times. These reconnections accelerate particles to near-light speeds, heat surrounding plasma, and produce bursts of light across the electromagnetic spectrum. In the environment near Sagittarius, a star, magnetic reconnection is not rare. It happens constantly, on scales that range from minutes to hours, affecting both the inner disk and the material further out. The structure of the accretion disk itself is far from uniform. The innermost regions are dominated by hot, dense plasma, moving in tightly packed orbits. Beyond that, the disk becomes more diffuse, with cooler gas and dust interacting with outflows and magnetic turbulence. The rotation is differential. Inner material circles faster than outer layers, creating shear that stretches magnetic field lines and builds energy in the system. Clumps of plasma collide and merge, sometimes forming temporary hotspots that flare brightly before dissipating. Every fluctuation in brightness, every shift in emission, originates from these intense, fast-moving interactions. Webb's observations captured these dynamics with unprecedented precision. Near-infrared imaging revealed the hottest plasma, showing the immediate response to magnetic activity and particle acceleration. Mid-infrared imaging traced slightly cooler regions, allowing researchers to see how energy propagates outward. By monitoring both wavelengths continuously, Webb recorded minute-by-minute variations, mapping the motion and heating of plasma in the inner disk. The data revealed that flickers and flares are not isolated events. They are the direct result of complex interactions between plasma, magnetic fields, and the black hole's gravity. The inner accretion disk is compressed into a narrow band close to the event horizon. Within this region, plasma moves so quickly that light from one side of the disk reaches observers slightly before light from the other side, creating subtle distortions in brightness and color. Relativistic beaming further amplifies these variations. Material moving toward the telescope appears brighter, while material moving away appears dimmer. These relativistic effects, combined with turbulence and magnetic reconnection, produce the rapid flickering captured by Webb's instruments. Magnetic fields dominate the inner disk. twisted lines of force store enormous amounts of energy, which is released when reconnections occur. Each reconnection event accelerates electrons and protons, producing bursts of synchrotron radiation in near-infrared light. Some flares occur every few minutes, reflecting local turbulence and rapid reconnection in small regions. Others grow into hour-long events, combining multiple reconnections and plasma flows into larger energy releases. The inner disk is a constant interplay of tension, motion, and heating, with gravity providing the underlying structure but magnetic forces controlling the dynamics. Clumps of plasma orbit at different speeds. Faster moving material closer to the black hole stretches and twists magnetic fields as it passes slower material farther out. These shearing motions increase magnetic tension and store energy in the disk. When the fields snap, that stored energy is released in bursts that heat the surrounding plasma and create bright flares. Minute-scale flickers trace the smallest events, while hour-scale flares reflect larger regions of magnetic stress, releasing energy simultaneously. Webb's continuous monitoring made it possible to see these processes in real time. Minute-by-minute fluctuations revealed localized reconnection events, showing plasma brightening and dimming as energy was released. Hour-long flares map the coordinated release of energy across larger regions. Short and long wavelength imaging allowed observers to track how energy moved from the hottest, fastest moving plasma to cooler material in the outer disk. The result was a clear, detailed view of how the accretion disk behaves under extreme conditions. The dynamics are not uniform across the disk. Some sections remain relatively stable, while others flare repeatedly. These hotspots orbit the black hole, twisting magnetic fields and interacting with surrounding plasma. When multiple regions flare at once, the combined emission can spike dramatically, creating bright surges in near-infrared light. The irregularity in timing, intensity, and location shows the chaotic nature of the disk. Energy release is unpredictable and constantly shifting. Accretion disks around black holes are often compared to rivers of plasma, but this analogy barely captures the reality. The inner disk is more like a hurricane of charged particles, twisting, colliding, and accelerating under extreme forces. Magnetic reconnection acts like lightning strikes within this storm, releasing bursts of energy that light up the disk in brief flashes. Minute-to-minute variations trace the tiniest of these events, while longer flares reveal the combined effect of multiple reconnections and turbulent plasma flows. The disk is heated unevenly. Plasma in some regions reaches tens of millions of degrees, producing strong near-infrared emission, while cooler regions farther out radiate primarily in mid-infrared. This temperature gradient, combined with differential rotation and magnetic activity, produces the flickering patterns observed. Rapid fluctuations indicate small, intense reconnection events, while gradual rises and decays correspond to the redistribution of energy through the disk. Plasma streams can collide, merge, or be ejected in jets or outflows. Although Sagittarius A star is relatively quiet compared to active galactic nuclei, the inner disk still produces bursts of matter and energy, guided by magnetic fields. These flows twist and stretch the disk, creating irregular patterns of brightness that Webb captured in extraordinary detail. Minute-scale changes correspond to local plasma interactions, while hour-scale flares reflect coordinated activity across a larger portion of the disk. Magnetic reconnection is the engine behind this flickering. Twisted field lines snap, sending electrons and protons racing along their paths. These particles emit synchrotron radiation, which Webb detects as bright near-infrared flares. As energy spreads outward, it heats surrounding plasma, producing delayed mid-infrared emission. The timing between short and long wavelength light allows the motion and acceleration of particles to be measured directly, revealing the physical processes at work near the event horizon. The inner accretion disk operates on multiple timescales. Minute-scale reconnections produce microflares, while overlapping events create hour-long flares visible across the infrared spectrum. This layered activity explains why flickering is constant, yet unpredictable. Plasma streams collide, magnetic fields reconnect, and energy is redistributed continuously. The black hole's surroundings are turbulent, unstable, and alive with extreme physics. Webb's observations turned what was once a vague model of the accretion disk into a detailed, measurable system. The continuous monitoring, multi-wavelength imaging, and high-resolution tracking captured the motion of plasma, the snapping of magnetic fields, and the propagation of energy outward. Minute-to-minute variability traced small reconnection events. Hour-long flares revealed larger-scale dynamics, and wavelength-dependent delays mapped energy transfer from hot inner plasma to cooler outer regions. Sudden energy release. The flickering was just the beginning. Then the flares hit. One moment the accretion disk is dim, almost invisible. The next, a spike of light erupts from the black hole's edge. Brightness doubles, triples, sometimes more, in mere minutes. Near-infrared lights flare first, tiny explosions racing along the plasma streams. Then mid-infrared follows, a delayed echo as the surrounding gas and dust heat up. The pattern repeats again and again. It's relentless. These weren't gentle, predictable pulses. The flares came in irregular patterns, some short and sharp, others stretching over an hour, morphing and twisting as if the disk itself was alive. Minute to minute, the brightness shifted, sometimes in one region, sometimes across multiple areas. It's chaos, but not random. Every spike, every lag is controlled by invisible magnetic forces, twisting and snapping lines of energy in the disk. Magnetic reconnection is the engine behind this violence. Imagine twisted magnetic field lines stretched to the breaking point, snapping suddenly. Electrons and protons accelerate to near-light speeds, heating the plasma and blasting energy into space. Every flare is essentially a lightning bolt in the black hole's accretion disk, but scaled up billions of times compared to anything on the Sun. These aren't just sparks, they are colossal bursts of energy ripping through a plasma storm. Some flares appeared almost like chains of explosions. One bright eruption could trigger a sequence of smaller bursts across nearby plasma clumps. Energy surges from one area to another, producing a cascade of light. The near-infrared spikes track the fastest, hottest material, while mid-infrared shows how that energy spreads, heating cooler material and creating a delayed response. The disk doesn't just flare, it communicates, transferring energy and pulses across its chaotic structure. Minute by minute, the variability is staggering. One small region brightens, then fades. Another flares slightly later, then dims. At the same time, larger areas can erupt simultaneously, producing flares visible across both wavelengths. The irregularity is breathtaking. No two flares are the same, and yet patterns emerge. Reconnection events dominate, moving like currents of energy along magnetic highways, accelerating particles, and sending plasma spiraling outward. This is where the comparison to solar flares becomes almost shocking. On the Sun, magnetic reconnections produce bursts of energy that light up the surface, eject plasma into space. Near Sagittarius A star, the same process is happening, but the scale is unimaginable. A single reconnection event can release energy equivalent to millions of solar flares, heating plasma to tens of millions of degrees, and accelerating particles at speeds approaching light. These aren't small events. They are colossal, sudden, and unstoppable. The timing between near and mid-infrared flares tells us how this energy flows. The hottest plasma closest to the black hole erupts first, releasing its energy into space almost immediately. Then the surrounding cooler plasma heats up, producing delayed mid-infrared light. This lag isn't just a curiosity, it's a measure of how energy moves through the black hole's environment. Each spike and delay maps particle acceleration, magnetic stress, and plasma heating in real time. Some flares are brief, lasting only a few minutes, while others stretch over hours. The disk can have multiple regions flaring at once, overlapping and creating patterns of light that shift and evolve. Minute-scale flickers trace the smallest reconnections, while hour-long flares show the combined effect of multiple events. It's a multi-layered, constantly changing storm, with energy constantly injected, released, and redistributed across the disk. Even though the black hole is quiet compared to a quasar, this energy release is constant and chaotic. Plasma streams twist, collide, and accelerate. Magnetic fields snap and reconnect. Bright flares erupt unexpectedly, then fade, only to flare again moments later. The inner accretion disk is alive with motion and energy. The flickers, spikes, and delayed responses are all signals of an environment dominated by magnetic forces, not just gravity. Minute-scale bursts show local reconnections, tiny explosions along magnetic field lines. Hour-long flares combine multiple reconnections into a single massive eruption, sweeping through the disk. The near-infrared shows the immediate, violent acceleration of particles. Mid-infrared reveals the energy spreading outward, heating cooler plasma and dust. This layered observation creates a real-time map of energy moving through a chaotic, superheated environment. It's almost impossible to overstate how extreme this is. Each flare releases unimaginable energy. Particles reach incredible speeds. Plasma heats to millions of degrees, and magnetic fields twist with a strength that dwarfs anything we can replicate on Earth. The flickers, the bursts, the irregular patterns, all of it points to a black hole that is constantly energized, constantly reshaping its surroundings, and constantly in motion. The environment near Sagittarius A star. The flickers and flares of Sagittarius A star are evidence of the invisible forces that control everything near the black hole. The gravitational pull of the black hole is extreme, yes, but it's the magnetic fields that dominate the environment in ways that redefine everything we thought we knew. Plasma moves, twists, and accelerates not just because it is caught in gravity's grip, but because magnetic fields channel, stretch, and snap it like cosmic rubber bands. The bright bursts Webb observed reveal that energy isn't released slowly or evenly. It explodes unpredictably across the disk. The accretion disk is a place of constant tension. Plasma spirals at nearly the speed of light, orbiting just outside the event horizon. Differential rotation, inner plasma moving faster than outer layers, stretches magnetic field lines, winding them tighter and tighter. When the stress becomes too great, these lines snap in reconnection events. Each snap releases massive amounts of energy almost instantly, accelerating particles to near-light speeds and heating surrounding plasma to millions of degrees. Near-infrared light jumps to life in bright spikes, signaling these violent releases of magnetic energy. What Webb captured was staggering. Minute-scale flickers are the smallest reconnection events, localized bursts of plasma heating and particle acceleration. But hour-long flares are combinations of multiple reconnections acting together, cascading across the disk. One flare might begin in the innermost plasma streams, erupt, and then trigger a chain reaction that spreads through other areas. Mid-infrared light follows seconds to minutes later, tracing how this energy propagates outward, heating cooler material and illuminating the surrounding environment. This timing is like a cosmic clock, measuring energy flow in real time. The speed at which particles accelerate is extreme. Electrons and protons caught in these magnetic reconnections are boosted to energies millions of times higher than anything achievable in Earth-based labs. They spiral along magnetic field lines, emitting synchrotron radiation, light caused by charged particles moving in intense magnetic fields. This radiation produces the near-infrared flares Webb recorded, the pulses of light that rise and fade in minutes. As the energy spreads outward, it interacts with cooler plasma, producing delayed mid-infrared emissions. The result is a cascade of light that maps the movement of energy across the disk. This is a black hole environment where gravity, plasma, and magnetic forces are intertwined in ways impossible to reproduce anywhere else. Gravity dictates the overall structure, forcing plasma into tight orbits. Magnetic fields dominate the dynamics within those orbits, twisting, snapping, and injecting energy continuously. Plasma is turbulent, unstable, and constantly heated by reconnections. Flares and flickers are the signatures of this energy transfer. Minute-scale flickers trace localized turbulence, while hour-scale flares reveal large-scale, coordinated magnetic activity. The inner accretion disk behaves differently from any simple model. It's not a smooth flow of material gradually spiraling inward. Instead, it is fractured into clumps, streams, and arcs of plasma. These clumps collide, merge, and separate, interacting with magnetic fields to produce sudden bursts of energy. Some flares originate from a single reconnection event in a small plasma pocket, while others combine multiple reconnections and plasma motions to create massive surges. Minute-by-minute observations show that no two flares are identical. Each eruption is unique, reflecting the chaotic environment in the disk. Energy spreads outward, not evenly, but in waves. Near-infrared light marks the hottest, fastest-moving plasma, closest to the black hole. Mid-infrared emissions trace cooler, slower material, revealing the propagation of energy. The delay between these wavelengths provides a direct measurement of how energy moves through the disk. Plasma streams brighten, magnetic fields snap, energy moves outward, and the cycle repeats continuously. Webb captured this unfolding drama in unprecedented detail, minute by minute, flare by flare. Even seemingly small reconnections release immense energy. A tiny burst in a localized plasma clump can heat surrounding material, trigger nearby reconnections, and produce a flare observable across both near and mid-infrared. Larger flares involve dozens, sometimes hundreds, of reconnections happening in rapid succession. The result is a multi-scale system where small and large bursts combine to create a constant pattern of chaos and energy release. The role of magnetic fields cannot be overstated. While gravity keeps the plasma in orbit, it is the magnetic tension that dictates the bursts, flares, and flickers. Twisted field lines act like springs, storing energy until the snap occurs. When reconnection happens, energy is released faster than the plasma can dissipate it, producing bright, sudden flares. These magnetic fields also control particle acceleration, shaping the direction, speed, and energy of plasma streams. The result is a black hole that is not only active, but constantly dynamic, unpredictable, and violent. The turbulence is extreme. Plasma clumps collide at near-light speeds, generating shocks and local heating. Magnetic reconnections occur in overlapping regions, creating flares that rise and fade unpredictably. Minute-scale flickers reveal tiny, local interactions, while hour-long flares show coordinated energy release across the disk. These patterns are not random. They are the natural outcome of a system dominated by magnetic energy, constantly being injected, redistributed, and radiated outward. Webb's observations also revealed the scale of energy involved. Some flares release energy equivalent to millions of solar flares. Electrons and protons reach relativistic speeds, emitting synchrotron radiation as they spiral along magnetic lines. The plasma heats to millions of degrees, causing bright near-infrared flares, while cooler material absorbs this energy and radiates delayed mid-infrared light. This sequence repeats continuously, minute after minute, hour after hour, forming a constant rhythm of extreme physics. The inner accretion disk is turbulent, unstable, and dynamic. Plasma streams twist, collide, and accelerate under the combined forces of gravity and magnetism. Flares erupt unpredictably, but with measurable structure. Magnetic reconnection is the engine driving these flares, producing the sudden bursts of energy captured by Webb. Minute-scale flickers trace small reconnections. Hour-scale flares reflect combined activity across multiple regions, and wavelength delays reveal the energy flow from inner to outer plasma. Sagittarius A star is a system defined by turbulence and energy. Gravity pulls matter inward, but magnetic fields dictate how that matter moves, how energy is released, and how plasma behaves. Brightness changes in minutes. Sagittarius, a star, isn't slow. In just a matter of minutes, its brightness spikes, dips, and surges again. One moment, the inner accretion disk is calm, almost invisible in near-infrared light. Moments later, it erupts, radiating energy as if someone flipped a cosmic switch. These rapid bursts aren't just spectacular, they're clues, direct evidence of how close to the black hole the action is happening. You see, the faster something flickers, the smaller the region producing that light. For Sagittarius A star, these flares rise and fall within minutes, meaning the emission zone is tiny on a cosmic scale. Just a few Schwarzschild radii from the event horizon. That's the very edge of no return, where gravity warps space and time, and where matter teeters on the brink of falling into the black hole. Every spike of light we see comes from plasma swirling perilously close to this point. These are not gradual changes. Near-infrared brightness can double, even triple, within just a few minutes. Minute to minute, the fluctuations map the motion of hot plasma as it races around the event horizon. Some flares rise so suddenly that the surrounding disk can barely respond before the energy dissipates. Others are slightly slower, giving the mid-infrared emission a chance to catch up, producing a delayed echo as heat spreads outward. This rapid timing is a direct measure of the intense physics operating in one of the universe's most extreme environments. The size of the emission region is astonishingly small. A few Schwarzschild radii, essentially a few times the radius of the black hole itself, is where these bursts originate. For Sagittarius A star, with a mass of roughly 4.3 million suns, that's just around 12 million kilometers across. In cosmic terms, that's microscopic. And yet, in that tiny region, plasma moves at nearly the speed of light. Magnetic fields twist violently, and energy is injected, released, and radiated in a constant cycle. These rapid brightness changes map the motion of matter on a scale smaller than the orbit of Mercury around the Sun, compressed into a region dominated by gravity and magnetism. Webb's near-infrared camera captures these minute-to-minute changes with unprecedented clarity. Every spike, every dip, every flare is recorded in real time, producing light curves that reveal the inner workings of the disk. Minute-scale fluctuations trace the tiniest reconnections in magnetic fields, where electrons accelerate to extreme energies, emitting synchrotron radiation. Longer flares, lasting tens of minutes to an hour, show multiple reconnections and plasma flows acting together, producing a larger, coherent burst of energy. Minute by minute, flare by flare, the black hole's activity is mapped like never before. The speed of these changes also tells us about the dynamics of the plasma. At this scale, hot matter orbits the black hole in fractions of an hour. Relativistic effects distort the timing and brightness of the light, amplifying some regions while dimming others. Parts of the disk moving toward us appear brighter due to beaming, while material moving away seems fainter. The interplay of motion, magnetism, and gravity produces a flickering pattern that is chaotic but measurable. Each spike of light is a probe of how plasma moves, heats, and radiates in this extreme environment. The smallest flares last just a few minutes, tracing local turbulence and tiny reconnection events in the magnetic field. Larger flares, spanning tens of minutes or longer, combine multiple reconnections across different regions of the inner disk. Each flare carries information about the density of the plasma, the strength and orientation of magnetic fields, and the velocity of particles accelerated near the event horizon. By tracking these rapid changes in brightness, Webb is essentially measuring the heartbeat of the black hole, observing processes that were completely invisible before. Minute-scale variability also reveals energy propagation in the disk. The fastest spikes come from the hottest, innermost plasma, closest to the black hole. Slightly slower changes in mid-infrared light show how that energy spreads into cooler, outer material. This lag allows the mapping of energy flows on scales of just a few Schwarzschild radii. Every flare provides a measurement: how fast particles accelerate, how energy spreads, and how the disk responds to magnetic stresses. These rapid fluctuations challenge our understanding of black holes, labelled quiet. Sagittarius A star was thought to be dormant compared to bright quasars, but the minute-scale variability proves that beneath the calm, extreme physics is happening constantly. The plasma is moving at relativistic speeds, magnetic reconnections inject energy in bursts, and the disk is far from uniform. Minute-to-minute changes show that energy release is not slow or gradual. It is instantaneous, chaotic, and concentrated near the event horizon. The inner accretion disk becomes a laboratory for extreme physics. Within a region only a few times the size of the black hole itself, plasma twists, collides, and accelerates under the influence of magnetic fields. Minute-scale spikes of light trace tiny reconnections, while longer flares track coordinated activity across multiple regions. Every rise and fall in brightness is a direct measurement of energy flow, particle acceleration, and magnetic dynamics. Webb allows these processes to be observed continuously. Unlike previous telescopes that captured only snapshots, Webb records the black hole's minute-to-minute variability without interruption. This provides unprecedented insight into how energy is generated, distributed, and radiated near the event horizon. It also reveals the scale. A tiny region in space is producing light bursts detectable across the galaxy. The timing, intensity, and wavelength dependence of these flares give a clear picture of how matter behaves under extreme gravity and magnetic stress. Minute-scale brightness changes are also critical for understanding the geometry of the disk. Different regions flare independently, revealing clumps of plasma orbiting at different speeds. Some regions produce isolated spikes, while others flare repeatedly in sequence, showing how energy propagates along magnetic field lines. These variations allow measurements of plasma density, velocity, and magnetic field strength at the very edge of the black hole. The scale and speed of these flares make them unique in astronomy. Nothing else changes this quickly on such a small scale around a supermassive black hole. They are not random anomalies. They are the natural outcome of plasma, gravity, and magnetic fields interacting at near light speed. Minute-to-minute variability defines the environment near Sagittarius A star, showing that energy release is constant, chaotic, and concentrated in a region only a few Schwarzschild radii wide. Each spike of brightness, every dip, and delayed mid-infrared response provides direct evidence of matter dancing on the edge of no return. Plasma is orbiting at extreme velocities, magnetic fields are snapping and reconnecting, and energy is released in bursts detectable millions of light years away. Webb has given the first continuous high-resolution view of this rapid activity, transforming our understanding of black holes from static shadows to dynamic living systems. The smallest flares, rising and falling within minutes, trace localized reconnections in the magnetic field. Larger flares, lasting tens of minutes or more, combine multiple reconnections and plasma flows. Short wavelength near-infrared light shows the hottest, fastest plasma. while slightly delayed mid-infrared emission tracks cooler regions. The timing between these wavelengths maps energy transfer, revealing not just motion, but the mechanisms powering the disk. Minute-to-minute variability also provides insight into the extreme physics of particle acceleration. Electrons and protons in these tiny regions reach relativistic speeds almost instantly, emitting synchrotron radiation as they spiral along magnetic field lines. Energy propagates outward, heating surrounding plasma and producing delayed emission. Flares overlap and combine, producing light curves that reveal the inner workings of the black hole in real time. This rapid variability, on a scale of just a few Schwarzschild radii, is the fastest ever observed for a supermassive black hole. It shows the disk is incredibly small, extremely dynamic, and magnetically dominated. Why previous telescopes missed this? For decades, Sagittarius A looked quiet, not inactive, not dead, just muted. Earlier telescopes pointed at the center of the Milky Way and saw a glow that barely changed. Slow rises, slow fades, long stretches of nothing at all. That calm wasn't real. It was an illusion created by limits. The problem wasn't the black hole. The problem was time. Most telescopes before Webb were simply too slow. Their observations were broken into short exposures. A few minutes here, a snapshot there, then long gaps while the telescope recalibrated, switched instruments, or moved on to another target. Anything that happened in between was lost. And near a black hole, almost everything important happens in between. Sagittarius A doesn't wait. The fastest activity near the event horizon unfolds on timescales of minutes, sometimes less. Bright flares rise sharply, peak and fade before older telescopes could even complete a clean exposure. By the time data came in, the event was already over. What remained was an average, smoothed out, flattened, stripped of detail. Earlier instruments blurred time together. Imagine watching a lightning storm, but your camera only takes one photo every 10 minutes. You'd miss the lightning entirely and conclude the sky was calm. That's what happened at the center of the galaxy for years. Noise made it worse. Earth-based telescopes had to look through the atmosphere. Turbulent air bends infrared light. Water vapor absorbs it. Heat from the ground adds background glow. All of this introduces noise, constant flicker that has nothing to do with the black hole itself. When the real signal changes fast and the noise is strong, the two blend together. Minute-scale variability disappears into static. Even space telescopes before Webb had limits. Some lacked the sensitivity to detect faint, fast changes. Others were tuned to wavelengths that missed the hottest plasma near the event horizon. Many could not observe continuously for long periods. They saw pieces, never the full sequence. Short observations hide fast physics. Sagittarius A doesn't flare on a neat schedule. There's no warning. A burst can appear suddenly, fade, and be followed by another minutes later. If the telescope wasn't watching at exactly that moment, the event simply didn't exist in the data. This led to a false picture. The black hole was labelled low activity, weak, quiet, dormant. Compared to quasars blasting energy across the universe, Sagittarius A seemed tame. But that comparison was based on incomplete information. The instruments weren't designed to catch rapid changes in a dusty, crowded galactic core. Crowding mattered too. The center of the Milky Way is packed with stars. Thousands of them orbit close to Sagittarius A. Earlier telescopes struggled to separate the black hole's faint infrared flicker from nearby stellar light. When brightness changed, it wasn't always clear what caused it. To avoid false detections, analysts averaged the signal over longer times. That averaging erased fast variability. Webb removed that limitation. Its resolution is sharp enough to isolate the black hole's emission from surrounding stars. Its sensitivity is high enough to detect subtle changes in brightness. And most importantly, it can stare continuously. No interruptions, no gaps, no smoothing over minutes of chaos. Webb doesn't just take pictures, it watches. Long, uninterrupted observation windows mean every flare is captured from start to finish. The rise, the peak, the decay, the pauses between bursts, the overlapping events. Nothing is averaged away. Nothing is lost to scheduling gaps. Previous telescopes saw fragments. Webb sees flow. Speed was the missing ingredient. Earlier instruments were designed to study structure, shapes, distributions, large-scale behaviour. Webb was built to track change. Its detectors read out quickly. Its stability allows hours of continuous monitoring. Its orbit keeps it away from Earth's heat and atmospheric interference. This turns Sagittarius A star into a monitored system instead of a distant object. Fast variability only becomes obvious when you can follow it second by second, minute by minute. When you can see one flare trigger another, when short wavelength spikes appear first and longer wavelengths respond later. Those timing relationships vanish when observations are chopped into pieces. Noise used to drown the signal. Webb's low background environment removes much of that interference. The black hole's flicker stands out clearly against the dark. What once looked like random noise resolves into structured bursts with consistent timing and behaviour. That clarity changes everything. Events that were once dismissed as statistical fluctuations now appear repeatedly, with similar shapes and durations. Patterns emerge, short flares cluster, larger flares build from smaller ones. Delays between wavelengths become measurable instead of speculative. Previous telescopes couldn't prove this because they couldn't see it cleanly or long enough. Webb can. It watches Sagittarius A star for hours without blinking. It tracks brightness changes across multiple infrared bands at the same time. It records the fastest variations ever measured from a supermassive black hole. That speed was always there. The universe didn't suddenly change. Our ability to see it did. Sagittarius A star didn't wake up. We finally caught it in the act. The black hole was never calm. We just weren't watching closely enough. Static image versus dynamic behaviour. When the Event Horizon Telescope released the first image of Sagittarius A star, the world saw a glowing ring surrounding a dark centre. It was historic. It confirmed decades of theory. A shadow where gravity is so strong that light cannot escape. A bright ring where hot matter races around the black hole before disappearing forever. The image became iconic almost instantly, but what that picture showed was not a moment in time. It was a blend of many moments layered together, compressed into a single frame. The Event Horizon Telescope cannot take a normal photograph. Sagittarius A star changes too fast. Matter near the event horizon completes orbits in minutes. The black hole flickers while the telescope is still collecting data. To produce an image at all, EHT had to combine hours of observations and mathematically reconstruct an average view. Every bright patch in that ring is not frozen motion. It is the sum of countless changes happening faster than the telescope could resolve individually. So what we saw was real, but incomplete. A time-smeared portrait of an object that never holds still. That is where James Webb enters the picture, not as a replacement, as a missing layer. Webb does not see the shadow itself. It does not resolve the event horizon the way EHT does. Instead, it watches the light coming from just outside that boundary and tracks how it changes moment by moment. Where EHT gives us shape, Webb gives us motion. Where EHT shows structure, Webb reveals behaviour. The difference matters because Sagittarius A star is not a steady system. The bright ring in the EHT image is not evenly glowing at all times. Parts of it brighten, fade, shift, and reappear on timescales of minutes. Those variations were averaged out in the EHT reconstruction. Webb does not average them out. Webb records them as they happen. This turns the EHT image from a static portrait into a dynamic environment. The glowing ring seen by EHT is made of hot plasma orbiting extremely close to the event horizon. That plasma does not move smoothly like a rigid wheel. It churns, it clumps, it accelerates and cools. Magnetic fields twist through it. Energy is released in bursts. Some regions suddenly become brighter than others, then fade again. Webb detects these brightness changes directly, tracking how fast they rise, how long they last, and how they move across wavelengths. Those changes explain why the EHT image is asymmetric. The ring is brighter on one side. That brightness is not permanent, it is the result of motion. Matter on one side of the black hole is moving toward us at near light speed, while matter on the opposite side is moving away. The EHT image captures that imbalance as a bright arc. Webb shows that the brightness itself fluctuates rapidly as plasma moves, accelerates, and releases energy. The EHT image looks stable because it has to. It is built from chaos. Webb reveals that chaos directly. When Webb watches Sagittarius A star, it sees continuous flickering from the same region that produces the EHT ring. Minute-scale brightness changes align with orbital timescales near the event horizon. The faster the flicker, the closer the emission is to the black hole. This connects the time behaviour seen by Webb to the spatial structure seen by EHT. They are observing the same physical region in different ways. EHT freezes space. Webb tracks time. This matters because black hole physics lives in motion, not stillness. The theories that describe event horizons, relativistic orbits, and plasma dynamics all predict rapid variability. Without time information, those predictions remain partially untested. Webb supplies that missing dimension. The EHT image confirms that Sagittarius A star has a shadow consistent with a supermassive black hole. Webb confirms that the environment around that shadow is violently active, constantly reorganizing itself on timescales of minutes. Together, they describe a system that is both geometrically stable and dynamically unstable. The black hole itself does not change. The matter around it never stops changing. The EHT image shows us where the edge is. Webb shows us what happens at that edge. Every flicker Webb records corresponds to plasma moving through the same region that produces the EHT ring. Every flare adds information about speed, temperature, magnetic strength, and particle acceleration. The static image gains meaning only when paired with dynamic data. Without Webb, the EHT ring is a snapshot without motion. Without EHT, Webb's flickering has no spatial anchor. What Webb explains that the EHT froze. The bright ring in the Event Horizon Telescope image was never evenly lit, and it was never supposed to be. One side shines harder, thicker, more intense, while the opposite side fades into a softer glow. That imbalance is not a flaw in the image and not a limitation of the reconstruction. It is physics, and James Webb finally shows why that brightness difference exists and why it never stays still. Matter orbiting Sagittarius A star does not drift slowly. Close to the event horizon, plasma races around the black hole at a large fraction of the speed of light. At those speeds, light itself stops behaving in intuitive ways. Emission is no longer symmetrical. Time stretches. Brightness amplifies. Direction matters. The side of the disk moving toward us appears brighter, hotter, and more energetic, while the side moving away appears dimmer, cooler, and subdued. This effect is known as relativistic Doppler boosting, and Webb's data shows it unfolding in real time, instead of being locked into a single, averaged image. When Webb monitors Sagittarius A star continuously, it detects rapid changes in brightness that sweep through infrared wavelengths in a consistent order. Shorter wavelengths spike first, followed by longer wavelengths moments later. These changes do not occur evenly across the disk. They cluster, they drift, they intensify on one side before shifting elsewhere. This behavior maps directly onto what the EHT image compresses into a single, bright arc. The asymmetry seen by EHT is not static structure. It is the time-averaged result of plasma repeatedly brightening as it approaches us, then fading as it swings away at extreme speed. Webb shows that the bright side of the EHT ring is not always the same region flaring. Instead, different pockets of plasma become dominant as they orbit. When a dense, energized clump swings toward our line of sight, its emission is amplified, its light is boosted, its brightness rises sharply. Minutes later, as it continues its orbit and begins moving away, that brightness drops and another region takes its place. Over hours, EHT blends all of those moments together, freezing the brightest average configuration into a single frame. Webb separates those moments and shows them one by one. This explains why the EHT image looks stable, even though the system itself is not. The black hole's gravity defines the shape of the shadow and the radius of the ring, but the brightness within that ring is governed by motion, not geometry. Webb's time-resolved observations reveal that the light near the event horizon is constantly being redistributed by orbital motion and relativistic effects. What EHT captures as a smooth arc is actually the statistical outcome of countless bright flashes and fades driven by near-light speed orbits. Doppler boosting is only part of the picture. Relativistic beaming also plays a role. As plasma accelerates, its emitted light becomes concentrated in the direction of motion. This means that emission is not radiated evenly in all directions. It is focused forward, like a headlight effect. Webb's data reveals how sudden brightness spikes correspond to moments when plasma motion aligns more directly with our line of sight. These spikes are brief because the alignment changes quickly as the plasma continues its orbit. EHT averages these headlight moments together, turning them into a persistent, bright region. Webb exposes their fleeting nature. Gravitational lensing adds another layer. Light emitted from the far side of the black hole is bent around it, contributing to the ring seen by EHT. That light is delayed and distorted. Webb detects timing differences between emission that originate closer to the black hole and those that travel longer, curved paths through warped spacetime. These delays subtly affect the brightness patterns Webb observes and help explain why some flares appear stretched or echoed across wavelengths. The EHT image contains this lensed light but cannot separate when it was emitted. Webb can. Together, these effects explain why the EHT image looks the way it does without invoking any exotic assumptions. The brightness asymmetry is not evidence of a permanent hotspot or a fixed structure. It is the natural outcome of relativistic motion, magnetic energy release, and gravitational lensing acting together near the event horizon. Webb shows that the brightest regions are temporary, repeatedly forming and dissolving as plasma circulates. EHT locks all of that motion into a single average geometry. Webb's infrared sensitivity is critical here because it tracks the heat emitted by energized plasma, rather than relying on radio wavelengths alone. This allows it to follow how energy is injected, redistributed, and lost as plasma moves through the inner accretion flow. Rapid heating events light up the near-infrared first, then fade into longer wavelengths as the plasma cools and spreads. These transitions line up with orbital motion predicted near the event horizon, reinforcing the connection between Webb's flickering light curves and the spatial ring seen by EHT. What once looked like a static imbalance now reveals itself as a constantly shifting pattern controlled by speed and direction. The black hole's shadow remains fixed, The ring remains the same size, but the brightness within it is always changing. Webb explains that change by showing how relativistic physics plays out second by second. EHT confirms where it all happens. The two instruments are observing the same environment from different angles of reality. One freezes space, the other tracks time, and when those views are combined, the bright arc around Sagittarius A star stops being a mysterious shape and becomes a measurable consequence of matter moving at extreme speed on the edge of the event horizon. No large-scale jets, and why that matters. When people think of supermassive black holes, they usually picture monsters that shoot gigantic jets across space, beams of energy so powerful they stretch for thousands or even millions of light years. Those images come from galaxies where the black hole is actively feeding, swallowing huge amounts of matter and converting that infalling material into focused, relativistic outflows. Sagittarius A star does not do that. There is no massive jet blasting out of the Milky Way's core, no colossal radiolobes carving through intergalactic space. And that absence is not a mystery of ignorance anymore. It is a physical consequence of how this black hole eats, how much it eats, and how efficiently it processes what little it receives. Sagittarius A star sits at the center of a galaxy that is relatively calm. The Milky Way is not undergoing a major merger. It is not ripping apart neighboring galaxies and funneling vast rivers of gas straight into its core. The fuel supply available to Sagittarius A star is thin and irregular. Instead of a steady inflow of dense gas clouds, it relies mostly on stellar winds. Massive stars near the galactic center constantly shed material, blowing gas outward as they age and evolve. Some of that gas drifts inward, captured by the black hole's gravity, but most of it escapes or disperses before it ever gets close. This feeding process is inefficient by nature. The gas arrives hot, fast, and chaotic. It does not cool easily. It does not settle into a dense, orderly disk the way it does in active galaxies. Instead, it forms a low-density, turbulent flow where much of the material never actually crosses the event horizon. It swirls, heats up, releases energy, and then gets flung back outward. The result is a black hole that is starved, not because the galaxy lacks matter, but because the matter arrives in the worst possible way for sustained growth. Jet formation requires more than just a black hole. It requires a specific alignment of conditions. There must be a strong, organized magnetic field threading the inner accretion disk. There must be a steady supply of infalling material to maintain pressure and structure. And there must be enough energy extraction, either from the disk or from the black hole's spin, to collimate that energy into narrow, stable beams. Sagittarius A star does not meet those conditions consistently. The magnetic fields near Sagittarius A star are strong, but they are tangled and unstable. Webb's observations show constant reconnection events, rapid energy release, and irregular brightness changes. That kind of magnetic environment is excellent at producing flares and variability. It is terrible at sustaining long, straight jets. Any attempt at large-scale collimation gets disrupted before it can stabilize. Energy is released locally in bursts instead of being channeled outward in a focused stream. Fuel supply plays a critical role here. In jet-producing systems, gas flows inward in a relatively steady stream. That steady pressure helps align magnetic fields and maintain a structured disk. Sagittarius A star receives fuel in spurts. A star passes close, sheds extra material, and the black hole briefly brightens. Then the supply drops again. The accretion rate fluctuates wildly over time. Without consistency, jets cannot form and persist. At the same time, Sagittarius A star is surprisingly efficient with the little fuel it gets. This is one of the most important points. Even though the total energy output is low compared to active galactic nuclei, the processes happening near the event horizon are extreme. A large fraction of the infalling energy is converted into heat. magnetic turbulence, and particle acceleration. That energy does not escape in jets. It stays trapped near the black hole, lighting up the inner region with rapid flickering and flares. This creates a misleading impression if you only look at total brightness. Sagittarius A star appears dim because it is underfed. But when you zoom in on the physics close to the event horizon, the system is anything but weak. The plasma is hot. The magnetic fields are intense. Particles are accelerated to near light speed. Energy is being released constantly, just not exported far from the black hole. In jet-dominated systems, much of the energy is carried away. The surroundings light up on enormous scales. In Sagittarius A star, the energy stays local. It churns the accretion flow instead of escaping it. Webb's observations of continuous variability and rapid flaring confirm this picture. The black hole is active on small scales and quiet on large ones, not because it lacks power, but because that power is trapped in a turbulent, inefficient feeding environment. Another factor is timescale. Jet activity can turn on and off over millions of years. There is evidence that Sagittarius A star may have been more active in the past. Faint structures in the Milky Way, like the Fermi bubbles, suggest episodes of higher energy output long ago. But right now, in the present epoch, the black hole is in a low accretion state. Webb is observing it during a phase where energy release is dominated by local plasma processes rather than large-scale outflows. This makes Sagittarius A star a rare laboratory. Most nearby supermassive black holes are either too quiet to study in detail or so active that their jets overwhelm the inner regions with radiation. Sagittarius A star sits in between, close enough to observe with precision, calm enough that the environment near the event horizon is not drowned out by jet emission, active enough that the physics is visible in real time. The absence of jets is not a failure of the system. It is what allows Webb to see what it sees. Without massive outflows dominating the signal, the infrared light from the inner accretion flow becomes detectable. Flickers, flares, and magnetic reconnections stand out clearly. The black hole's behavior is written directly into the light curve instead of being masked by distant lobes and beams. Sagittarius A star is different because it is underfed but efficient, turbulent but nearby, magnetically active but structurally unstable. It does not convert its energy into grand cosmic architecture. It converts it into rapid motion, heat and variability right at the edge of the event horizon. That combination makes it unlike the textbook examples of jet-driven supermassive black holes and turns it into one of the most revealing objects in the sky. How Sagittarius A star compares to M87 star and what makes the Milky Way's core unique. To understand why Sagittarius A star behaves the way it does, it helps to place it next to the most famous comparison point we have, M87 star. Both are supermassive black holes. Both have been imaged by the Event Horizon Telescope. Both sit at the centers of large galaxies. And yet beyond that, they could not behave more differently. M87 star lives in a massive elliptical galaxy at the heart of the Virgo cluster. Its environment is rich, dense, and violent. Gas flows toward its center in enormous quantities, fed not just by stellar winds, but by large-scale galactic interactions and cooling flows from surrounding hot gas. The result is a black hole with a steady, powerful fuel supply. That fuel settles into a more organized accretion structure and supports strong, large-scale magnetic fields that remain stable over long periods. Sagittarius A star does not have that luxury. The Milky Way is a spiral galaxy with a comparatively calm core. Gas exists, but it is fragmented, turbulent, and mostly tied up in stars rather than freely flowing toward the center. What reaches Sagittarius A star arrives indirectly, blown off nearby stars in irregular bursts. The feeding is sporadic and inefficient. This difference in supply sets the tone for everything that follows. In M87 star, the steady inflow of matter allows energy to be exported. The black hole launches a jet that extends thousands of light years into space. That jet is narrow, focused, and persistent. It carries away enormous amounts of energy and angular momentum, shaping the surrounding galaxy and beyond. The environment near the event horizon is still extreme, but much of the system's power is channeled outward. The inner accretion flow is not the main stage, the jet is. Sagittarius A star operates in the opposite regime. With no stable, sustained inflow, it cannot maintain the magnetic structure required to collimate a jet. Energy stays close to the black hole. Instead of being funneled into a narrow beam, it is dissipated through turbulence, magnetic reconnection, and particle acceleration in the inner accretion flow. The result is intense local activity without large-scale impact. This difference shows up directly in observations. M87 star's emission is dominated by jet-related processes. Its brightness varies, but much of what we see is tied to structures that persist over long timescales. Sagittarius A star's emission is dominated by short-term variability. Minute-scale flickering, hour-scale flares, irregular bursts that appear and vanish quickly. Webb captures this clearly. The signal from Sagittarius A star is restless, constantly shifting, because the energy has nowhere else to go. The mass difference matters too, but not in the way people often assume. M87 star is far more massive than Sagittarius A star. That means the characteristic timescales near its event horizon are longer. Orbits take days instead of minutes. Changes happen more slowly. Variability is stretched out in time. Sagittarius A star, being smaller, evolves faster. The same physical processes unfold, but compressed into minutes and hours instead of days and weeks. This makes rapid variability easier to detect if you have the right instrument. Distance plays a role as well. Sagittarius A star is close, astronomically close. That proximity allows Webb to resolve faint changes in brightness that would be lost in more distant systems. M87 star is much farther away. Even though it is more massive and more energetic, its distance smooths out fine details. Subtle, fast variations are harder to isolate. Sagittarius A star benefits from being both small and nearby, placing its most violent region within reach of precise, time-resolved observation. The surrounding environment is also different. M87 star sits in a galaxy filled with hot, diffuse gas that interacts with its jet and feeds back into the accretion process. Sagittarius A star sits in a crowded stellar neighborhood. Stars orbit close, their winds collide, gas streams intersect. This creates a chaotic feeding zone where material arrives with different speeds, directions, and temperatures. The inner accretion flow reflects that chaos. Webb's observations of irregular flaring and non-stop flickering are a direct consequence of this environment. What makes the Milky Way's core unique is not just that its black hole is quieter on large scales, but that its small-scale behaviour is exposed. There is no overpowering jet to dominate the signal. There is no thick, luminous disk hiding the inner region. What we see is the raw interaction between gravity, plasma, and magnetic fields just outside the event horizon. Sagittarius A star acts like a laboratory version of a supermassive black hole. The same fundamental physics applies as in M87 star, but stripped of the large-scale distractions. Energy is not exported. It is processed locally. Motion is not smoothed out over vast distances. It is visible directly in rapid variability. This is why Webb's observations matter more here than they would in many other galaxies. The Milky Way's black hole is not the brightest or the most powerful, but it is the most revealing. Its differences from M87 star are not weaknesses. They are what allow us to watch extreme black hole physics unfold in real time, close enough to measure, quiet enough to see, and active enough to matter. What this means for black hole physics. For a long time, black hole physics relied on stability, not because the universe demanded it, but because the math needed it. Early models assumed smooth disks, steady inflow, slow changes averaged over time. Matter spiraled in, energy radiated out, angular momentum gradually lost. Those assumptions were not careless. They were necessary. Observations could not resolve rapid changes close to the event horizon, so theory filled in the gaps with equilibrium. Webb removed that equilibrium. The light curves coming from Sagittarius A star do not show a steady system with minor fluctuations. They show constant disruption. Brightness rises and falls on minute timescales. Energy release is irregular. Emission zones shift rapidly. This behavior directly validates accretion models where magnetic fields dominate the dynamics instead of acting as a secondary effect. Magnetically driven accretion has existed in simulations for years. In those models, magnetic fields are not passive threads frozen into the plasma. They actively shape motion. They transport angular momentum outward. They trigger reconnection events that heat plasma explosively. They create turbulence that prevents matter from settling into a calm disk. Webb's observations match those predictions closely, not in abstract trends, but in timing, variability, and wavelength behavior. The rapid flickering shows that energy is being injected locally and repeatedly. That does not happen in steady disk models. A smooth disk radiates predictably. It does not produce frequent sharp flares unless something disrupts it. Webb shows that disruption is the norm near the event horizon, not the exception. Magnetic reconnection provides a physical mechanism that explains both the timing and intensity of the observed flares without invoking additional structures or exotic physics. Older steady disk assumptions struggle here. In those models, angular momentum loss is slow and continuous. Matter gradually spirals inward through viscosity-like processes. That picture cannot easily produce minute-scale variability originating just a few Schwarzschild radii from the black hole. The timescales are too short. The region is too compact. Webb's data forces a re-evaluation of how angular momentum is actually removed from infalling material. Magnetic turbulence offers a solution. Instead of smooth transport, angular momentum is redistributed through chaotic magnetic stresses. Plasma elements exchange momentum rapidly as field lines twist and reconnect. Some material loses angular momentum abruptly and plunges inward. Other material gains it and is pushed outward. This naturally produces rapid, uneven emission, exactly what Webb observes. Energy transport is affected in the same way. In steady models, energy flows outward gradually through radiation. In magnetically dominated flows, energy is stored in magnetic fields and released suddenly. Webb's infrared flares are consistent with this picture. Short wavelength spikes appear first, tracing sudden particle acceleration. Longer wavelengths follow as that energy spreads, heat surrounding plasma, and dissipates. This layered response is a signature of magnetic energy release, not steady heating. These observations also constrain where the emission comes from. The fastest variability limits the size of the emitting region to just a few Schwarzschild radii. That places the source extremely close to the event horizon. At those distances, general relativity is not a correction. It is the governing framework. Time dilation, gravitational redshift, and relativistic motion all shape what Webb detects. This has direct implications for plasma physics under extreme gravity. The plasma near Sagittarius A star is not behaving like laboratory plasma or even like plasma in stars. Particle distributions are non-thermal. Magnetic fields are strong enough to dominate pressure. Reconnection occurs in curved space-time, where orbital motion and relativistic effects alter how energy is released and transported. Webb's data provides real constraints on these conditions instead of relying purely on theoretical estimates. Simulations now have something they did not have before: time-resolved observational benchmarks. General relativistic magneto-hydrodynamic simulations have long predicted flickering, turbulence, and magnetic reconnection near black holes. But many parameters were unconstrained: field strength, plasma density, heating rates, cooling times. Webb's observations narrow those ranges. Models that produce variability too slowly or too smoothly no longer match reality. This refinement matters because GRMHD simulations are used to interpret everything from black hole growth to jet formation. If the inner accretion flow is more chaotic and magnetically dominated than previously assumed, then energy conversion efficiencies change, angular momentum loss rates change, the fraction of material that actually reaches the event horizon changes. These are not small corrections. They affect how black holes evolve over cosmic time. The absence of steady behavior near Sagittarius A star also informs how accretion states are classified. Low luminosity black holes were often treated as scaled-down versions of active ones. Webb shows that the scaling is not simple. The physics is different in kind, not just degree. Magnetically dominated, low-density flows behave differently from dense, luminous disks. Applying the same assumptions across both regimes introduces errors that now have observational consequences. The data also forces a rethink of how emission models are constructed. Matching a single image or spectrum is no longer enough. Models must reproduce variability across wavelengths and timescales simultaneously. They must explain why near-infrared flares lead mid-infrared emission. They must produce the correct delays, amplitudes, and irregular patterns. This sharply narrows the space of viable theories. Perhaps most importantly, Webb shows that black hole environments cannot be understood through averages alone. Time matters. Dynamics matter. The physics near the event horizon unfolds continuously, not as a stable background with occasional disturbances. That realization does not add speculation. It removes approximation. Black hole physics now has direct evidence that magnetic fields are central actors, not supporting characters. Accretion is not a smooth conveyor belt. It is a turbulent, magnetically driven process where energy and angular momentum are exchanged violently and unpredictably. Webb's observations do not invent new theory. They confirm which existing theories survive contact with reality. Sagittarius A star becomes a calibration point. Any physical model of black hole accretion must now explain its rapid variability, compact emission region, wavelength-dependent timing, and persistent magnetic activity. If it cannot, it is incomplete. That constraint propagates outward, influencing how black holes are modeled across the universe, not through speculation, but through measured behavior in the strongest gravitational environment we can observe directly. Could Sagittarius A star ever wake up? Sagittarius, a star, is active right now, not in the way quasars are active, not in the way jet-launching black holes dominate their galaxies, but active in the only way a black hole truly can be, by interacting with whatever matter manages to reach it. The question is not whether it does anything. The real question is whether it could ever do much more than it's doing now. To answer that, the first place to look is the past, because the Milky Way itself carries physical records of what Sagittarius A star has already done. These records are not subtle. They are enormous, structured, and measurable, and they do not rely on interpretation or theory alone. Far above and below the plane of the Milky Way sit two gigantic lobes of high-energy radiation known as the Fermi bubbles. They stretch tens of thousands of light-years into space. They glow in gamma rays. Their edges are sharp. Their symmetry is striking. and their energy content is far too large to be explained by normal stellar processes alone. The simplest explanation is also the most consistent one. Sagittarius A star was more active in the past and released a massive amount of energy into the galaxy's halo. Not as a long-lived quasar, not as a sustained jet system like M87 star, but as a powerful outburst. Something fed it. For a limited time, the black hole responded. Then the fuel ran out and the activity faded. The timing matters. The Fermi bubbles are not ancient relics from the early universe. They are relatively young on cosmic timescales, likely formed within the last few million years. That is recent. That places the activity firmly within the Milky Way's modern history. Sagittarius A star did not need to become a quasar to leave these marks. It only needed more fuel than it has today. X-ray echoes reinforce this picture. Observations of dense molecular clouds near the galactic center show reflected X-ray emission that cannot be explained by current activity levels. These clouds act like mirrors. They light up when exposed to strong X-ray radiation, then fade as that radiation passes. By measuring the brightness and delay of these echoes, astronomers can reconstruct past flares from Sagittarius A star. The result is clear. The black hole was brighter in X-rays a few hundred years ago than it is today. Not brighter by orders of magnitude compared to quasars, but significantly brighter than its present state. Enough to illuminate nearby clouds. Enough to prove variability on timescales much longer than human observation, but much shorter than galactic evolution. This establishes an important fact. Sagittarius A star does not exist in a permanently quiet state. Its activity level changes when its fuel supply changes. The black hole itself does not switch modes spontaneously. The environment controls the behavior. Webb's data fits cleanly into this picture. The observations show that Sagittarius A star is still in a low accretion regime. The mass intake is small. Stellar winds remain the dominant source of fuel. Most of that material never reaches the event horizon. It heats up, interacts magnetically, releases energy locally, and escapes. The rapid flickering and flaring Webb seas are signs of efficiency, not abundance. The black hole is processing very little mass very intensely. There is no indication in the data of a transition toward a high accretion state. No long-term brightening trend. No increase in average luminosity. No structural changes that would suggest the formation of a dense, stable accretion disk. The system remains magnetically turbulent and fuel poor. This rules out any imminent quasar phase. A quasar requires sustained, high-volume gas inflow. That does not exist in the Milky Way's center right now. The galaxy is not undergoing a major merger. There is no massive cold gas reservoir spiraling inward. The large-scale structure of the Milky Way does not support that kind of feeding. For Sagittarius A star to significantly wake up, something external would have to change. The black hole cannot create fuel. It can only react to it. One possible trigger would be a massive gas inflow. This could happen if a large molecular cloud were driven toward the galactic center. Such clouds exist, but their orbits are complex, and most are stabilized by angular momentum and stellar feedback. Delivering a substantial fraction of one directly into the inner parsec would require a strong disturbance, such as a galactic interaction or an internal dynamical instability on a much larger scale. There is no evidence that such a process is underway. Another possibility is a stellar disruption event. If a star wanders too close to the black hole, tidal forces can tear it apart, feeding a sudden surge of material into the accretion flow. These events are real and have been observed in other galaxies. If one occurred near Sagittarius A star, the black hole would brighten dramatically for months or years. It would not become a quasar, but it would become unmistakably more active. Even here, scale matters. A single disrupted star provides a temporary spike, not a long-term transformation. The black hole would flare, then settle back down once the debris is consumed or dispersed. The galaxy would notice. Life on Earth would not. The most extreme scenario would involve a sustained change in the Milky Way's structure, such as a merger with another galaxy rich in gas. That would fundamentally alter the fuel supply to the galactic center. Over millions of years, Sagittarius A star could transition into a much more active state. This is not speculation. It is observed in other galaxies. But it is not a near-term possibility. The Milky Way's next major merger is far in the future, and even then, the outcome would depend on many variables. What Webb shows us is that Sagittarius A star is responsive, not dormant. It reacts quickly to changes in its immediate environment. Its variability proves that. Its past activity proves that. But responsiveness is not the same as inevitability. Without new fuel, the system stays where it is. There is no runaway process here, no threshold being crossed, no hidden buildup of energy waiting to be released. Black holes do not store power, they process mass. When the mass supply is low, activity stays local and transient. When the supply increases, activity scales with it. This is why there is no fear-mongering attached to this question. The physics does not support sudden catastrophic awakening without an external cause. Sagittarius A star is not ticking, it is reacting. The evidence points to a black hole that has flared before, will flare again, and will continue to fluctuate as long as stars orbit nearby and gas drifts inward. Webb's data confirms the present state clearly: low intake, high efficiency, no trajectory toward extreme luminosity. Sagittarius. A star current behavior already exposes the physics that governs black holes everywhere. And if it ever does receive more fuel, the same rules will apply, only scaled by supply. Just gravity, plasma, and energy responding to changing conditions in the core of a galaxy. The future observations already planned. What James Webb saw was not treated as a one-off moment. From the start, the observations of Sagittarius A star were designed as an opening move, not a conclusion. The behavior Webb captured made one thing immediately clear. This black hole changes too fast and too often to be understood through isolated campaigns. Watching it once is not enough. It has to be monitored repeatedly over time, across wavelengths and in coordination with other instruments that can probe different layers of the same environment. That is exactly what is now planned. Continued monitoring with Webb is already built into future observation cycles. The goal is not simply to repeat what was done before, but to extend it in duration, cadence, and context. Longer monitoring windows allow rare events to surface. Short flares are common, but larger flares are not. They may occur less frequently, but when they do, they carry far more information about how energy builds up and is released near the event horizon. Capturing one from beginning to end would provide direct constraints on magnetic field strength, plasma density, and particle acceleration limits that cannot be extracted from smaller events alone. Repeated observations also allow scientists to track whether the variability patterns themselves change. If Sagittarius A star enters a slightly higher or lower accretion state, the statistics of its flickering will shift. The rate of flares, their brightness, their duration, and their wavelength delays will respond. Webb is sensitive enough to detect those changes even if the overall luminosity remains low. This turns the telescope into a long-term monitor rather than a discovery snapshot. Another major focus of upcoming Webb campaigns is polarization. Light does not only carry brightness and color, it also carries information about orientation. Polarization reveals how electromagnetic waves are aligned, and that alignment is shaped directly by magnetic fields. Near a black hole, where magnetic forces dominate plasma motion, polarization becomes a powerful diagnostic tool. Polarized infrared light can trace the structure and coherence of magnetic fields in the inner accretion flow. Changes in polarization angle over time can reveal how magnetic field lines twist, reconnect, and reorganize. Sudden shifts may correspond to reconnection events. Gradual rotations may trace orbiting plasma structures. Webb's sensitivity makes it possible to measure polarization even in a source as faint and variable as Sagittarius A star. This matters because magnetic fields are the least directly observable ingredient in black hole physics. Gravity is inferred from motion, plasma temperature from emission, density from brightness. Magnetic fields are usually inferred indirectly through models. Polarization data reduces that uncertainty. It provides direct observational constraints on field geometry and strength close to the event horizon. Webb will not be doing this alone. The future of Sagittarius A star observations is coordinated by design. Different telescopes see different physical processes, and the black hole does not separate those processes neatly. Coordinated campaigns allow the same flare or variability episode to be observed simultaneously across the electromagnetic spectrum. Chandra plays a key role here. While Webb observes infrared emission from hot plasma and dust, Chandra tracks high-energy X-rays produced by the most extreme particle acceleration events. When a flare appears in infrared, X-rays may follow or precede it, depending on the mechanism involved. Matching the timing between infrared and X-ray signals helps determine whether the same particle population is responsible for both, or whether separate processes are at work. X-ray observations also probe the hottest, most energetic regions closest to the black hole. They are sensitive to shocks, extreme heating, and non-thermal particle distributions. Coordinated Webb and Chandra observations allow scientists to follow how energy moves from magnetic reconnection into particle acceleration and radiation, across different energy bands, without relying on assumptions. ALMA adds another layer. Operating at millimeter and sub-millimeter wavelengths, ALMA observes cooler plasma and larger-scale structures around Sagittarius A star. It bridges the gap between the immediate vicinity of the event horizon and the surrounding accretion environment. ALMA can track changes in density, structure, and magnetic field orientation farther out, providing context for the rapid variability Webb sees closer in. When ALMA detects changes in polarization or brightness at millimeter wavelengths at the same time Webb sees infrared flares, it suggests a physical connection between inner and outer regions of the accretion flow. Energy released near the event horizon does not stay isolated. It propagates outward, heating and disturbing surrounding material. Coordinated observations allow that propagation to be traced directly. The Event Horizon Telescope remains central to this effort, even though it does not observe continuously. Planned upgrades will improve its sensitivity, resolution, and imaging speed. More stations, better receivers, and higher observing frequencies will reduce the amount of time averaging required to produce images. This opens the possibility of detecting changes in structure over shorter timescales than before. As EHT imaging improves, its static snapshots will become less static. While it will never match Webb's time resolution, future EHT observations may begin to detect shifts in brightness patterns within the ring itself. When paired with Webb's light curves, those shifts can be tied to specific variability events. The spatial structure frozen by EHT gains a time axis. One of the most sought-after targets in future observations is an orbital hotspot. Simulations predict that dense clumps of plasma can form and orbit close to the event horizon before dissipating. These hotspots would produce periodic signals as they move, with brightness modulated by relativistic effects. Webb has already seen hints of behaviour consistent with orbiting features, but longer monitoring is needed to isolate clear periodicity. Catching a well-defined orbital hotspot would allow direct measurement of orbital speed and radius. That provides an independent test of general relativity in the strong field regime. It would also constrain the spin of the black hole because orbital dynamics close to the event horizon depend on rotation. This is not speculative. The physics is clear. What remains is capturing a clean enough signal. Larger flare events are another priority. Smaller flares are common, but they may represent only local reconnection events. Larger flares likely involve more extended regions and stronger magnetic restructuring. Observing one with full multi-wavelength coverage would reveal how energy builds up over time before release, how rapidly it is converted into radiation, and how it dissipates afterward. Magnetic field mapping ties all of this together. Combining polarization data from Webb, ALMA, and EHT allows magnetic field structure to be reconstructed across scales. This turns abstract magnetic models into testable frameworks. Instead of asking whether magnetic fields matter, observations now focus on how they are arranged, how they evolve, and how they drive observable behavior. The broader impact of these future observations extends beyond Sagittarius A star. The Milky Way's black hole is the only supermassive black hole close enough to be studied at this level of detail. What is learned here becomes the reference point for interpreting distant systems, where only partial data is available. Variability patterns, polarization signatures, and energy transport mechanisms identified at Sagittarius A star inform how other low luminosity black holes are modelled across the universe. Momentum matters here. Webb did not answer a single question and move on. It exposed a system that demands continuous attention. Every new observation refines the physical picture. Every coordinated campaign reduces uncertainty. The future observations already planned are not about chasing surprises. They are about fully characterizing a black hole that is finally observable as a dynamic physical system rather than a static object.